In this video we will continue with the next stage of planet Earth, the Archean Eon. This is episode 2 of the series. If you enjoy these videos, please feel free to leave a like and or subscribe. But for now, sit back, relax, and enjoy. Before the story begins, there is quiet. Not the quiet of an empty room, or the quiet of a sleeping house, or even the quiet of a forest in deep winter. This is a different kind of quiet altogether. This is the quiet of before sound had anything to travel through, before light had anything to strike, before the very idea of a world had taken shape. In this quiet, there is only potential. And potential, as we will come to learn, is perhaps the most powerful thing there is. This is the story of Earth. Not of the Earth as we know her, not the blue and breathing world wrapped in clouds, not the world of oceans and forests and creatures stirring in the dark. We will get there. We will get there in time. But tonight, we begin at the very beginning. We begin in fire. Close your eyes, if you like. Let your body settle. Let the weight of the day fall away from you like dust from a ledge. Because what you are about to hear is a very long story, the longest story there is, and the best way to receive a long story is gently, and without hurry. We are going back. 4.5 billion years, give or take. Before the dinosaurs. Before the fish. Before the first trembling cell that dared to call itself alive. Before even the oceans. We are going back to a time so remote that the word ancient feels almost laughably insufficient. The geologists have a name for where we are going. They call it the Archean, from the ancient Greek, archeos, meaning beginning. The primordial. The first. And it earns the name. The Archean Eon stretches from approximately 4 billion years ago to 2.5 billion years ago. 1.5 billion years of time. Pause on that for a moment. 1.5 billion years. The entire history of complex animal life on this planet, every fish, every fern, every dinosaur, every mammal, every human civilization fits comfortably inside about 600 million years. The Archean is more than twice that long. It is deep time. It is time so vast that the human mind was simply not built to hold it whole. But we can feel the edges of it. We can trace its shape in the dark. She did not always look like this, our Earth. She was not always blue. She was not always gentle. She was not, in any sense we might recognize, hospitable. In those earliest days she was something altogether more violent, more raw, more honestly elemental than anything living memory has ever witnessed. She had just been born. Her birth, and it is fair to call it that, even if the metaphor is imprecise, happened in the debris field of a young star. Our sun, then only newly ignited, sat at the center of a vast spinning disk of gas and dust and rock. Slowly, over tens of millions of years, gravity gathered the scattered material into clumps. Clumps became boulders. Boulders became planetesimals, bodies the size of small moons, careening through the darkness, colliding, merging, shattering and merging again. Earth grew by accumulation. By collision. By the patient, brutal arithmetic of gravity. In these earliest years, just before the Archean properly begins, she was struck by something enormous. A body roughly the size of Mars. The scientists who study these things have given it a name. Theia collided with the young Earth in an impact so catastrophic that it defies easy description. The energy released was incomprehensible. Both bodies were partially vaporized. Material was flung outward in a vast ring of molten debris, which over time, over thousands of years coalesced into a new, second body, circling close. The Moon. Her companion. Her tidal anchor. The body that would, for billions of years, tug at her seas and slow her spin and keep her tilted at just the right angle to have seasons. The Moon was born from Earth's own wound. Perhaps that is worth sitting with for a moment. Now we enter the Archean in earnest. 4 billion years ago. The impact has faded. The debris has settled. The Earth hangs in space, and there is no gentle way to say this molten. Her surface is a global ocean of liquid rock. Magma, not water, stretches from pole to pole. She radiates heat like a coal plucked from a fire, glowing a dull and terrible orange red, lit from within by the decay of radioactive elements and the residual heat of her own formation. If you could stand above her, if such a thing were possible, she would look something like Jupiter's moon Io today, only larger, only hotter, only more savage. There is no solid ground. Not yet. There is no sky that could be breathed. There is no water standing in pools. There is simply heat and rock, and the slow churning of a world working out what it wants to become. She is not passive in this. That is the thing to understand about Earth, even now, even from the very start. She is not a rock that things happen to. She is a system, dynamic, self-regulating, restless in ways that will define everything that comes after. Even in her molten state, she is already sorting herself out. Gravity is at work inside her. The heaviest elements, iron, nickel, are sinking toward the center, pulled down by their own weight through the viscous rock. The lighter silicates rise. Over millions of years, this process of differentiation separates the interior of the Earth into distinct layers, a dense metallic core beginning to solidify at the very center, a thick mantle of rock in various states of melt and solid, and eventually the suggestion of a crust beginning to form at the surface, where the heat radiates away into the cold of space. She is, even now, becoming organized. Even in her chaos, she is learning structure. The core is particularly important. As it solidifies and the liquid outer core churns around it, driven by the heat still bleeding from the center, it generates something remarkable. A magnetic field. An invisible but vast envelope of electromagnetic force that wraps around the entire planet, deflecting the charged particles streaming out from the sun. The solar wind, if left unchecked, would strip away an atmosphere. It would scour a world bare. The magnetic field is Earth's first shield, her first act of self-preservation. And it works. It has worked for billions of years. It works still, to this day, invisible and essential and almost completely unremarked upon by the creatures it protects. The atmosphere in the early Archean is nothing like what we breathe today. There is no oxygen. None at all. The air is perhaps too kind a word for what surrounds the young Earth is a thick, toxic mixture of volcanic gases, water vapor, carbon dioxide, nitrogen, methane, hydrogen sulfide, ammonia. It is hot. It is chemically reactive. It bears no resemblance to the clean, life-sustaining blend we take for granted with every breath. And yet, even this poisonous shroud is something. It is better than nothing. It is a blanket, trapping some of the heat that would otherwise bleed away into space. It is a pressure that keeps water when water eventually arrives from simply boiling off into vacuum. It is the beginning of a sky. The water comes from several places at once. Some of it was always here, locked into the rocky minerals that built the planet, now outgassing from volcanoes as steam. Some of it arrives from beyond, carried in by the relentless bombardment of icy comets and water-rich asteroids that continue to pepper the inner solar system for hundreds of millions of years. This period is so intense that scientists call it the late heavy bombardment. Imagine the sky not as something still and distant, but as an active place, objects moving in it, trailing fire, striking the surface with a regularity and ferocity that would be impossible to ignore. Each impact releases energy. Each impact, on a world with water, creates a local sea of steam and shattered rock. But the water accumulates. Despite the heat. Despite the bombardment. It begins to gather. Somewhere around 4 billion years ago, perhaps a little after, perhaps a little before, the geological record at these distances becomes uncertain, becomes suggestive rather than definitive. The surface of the Earth cools enough. Just enough. The first thin crust forms over the ocean of magma, like ice forming on a pond, fragile and prone to shattering, but real. The first genuine solid rock. And then for the first time in the history of this world it rains. Not a gentle rain. Not the quiet rain that falls on a summer evening and smells of earth and green growing things. This is something else entirely. The atmosphere is saturated with water vapor, held in suspension by the volcanic heat, and as the surface cools, all of that water vapor begins to condense at once. The rains that fall in the early Archean are global. They are torrential. They fall for millions of years. They fill the basins of the young crust. The oceans are born. Let that image settle for a moment. The first rain falling on a world that has never known it. The first drop striking rock that has never been wet. The steam rising from the impact, the slow filling of low places, the way water finds its level as it always does, as it always will. Earth, in this moment, is becoming something new. She is no longer purely a world of fire and rock. She has a surface that is partly liquid, partly solid. She has a sky, however harsh. She has the raw ingredients of something. She does not know it yet. Of course she doesn't. She is not conscious. She is not thinking. She is a planet of 4.5 billion tons of rock and metal, and now, for the first time, water following the laws of physics as faithfully as any other body in the universe. And yet there is something that feels, when you trace the story from this distance, like intention. Like direction. An arrow pointing somewhere, even if no one has yet decided where it leads. This is the world at the dawn of the Archean. Hot, wet, volcanic beyond all modern reckoning. An atmosphere of poison. Oceans that would be scalding to any life we know. A sky lit not by blue daylight but by a permanent reddish murk, filtered through volcanic haze, the sun appearing dimmer than it does today paradoxically, because the young sun burned cooler than the middle-aged star it has since become. It is not a comfortable world. It is not a welcoming world. It is, by any human measure, a hostile and overwhelming place. But it is alive in a way. Not biologically. Not yet. But dynamically. Energetically. The planet is working. Heat is driving circulation in the mantle. Volcanoes are building crust and then subducting it back down again. The oceans are interacting chemically with the rock beneath them. The atmosphere is being shaped and reshaped by volcanic outgassing and by the slow filtering effect of the magnetic field above. Everything is in motion. Everything is in conversation. Everything is, in its way, preparing. We are 4 billion years from this moment. We are lying down in the dark, breathing quietly, while the oldest story there is begins to unfold. And though we are very far from the part of the story where we appear, though the distance between that scalding young world and us, sitting here, in the quiet of this night, is almost inconceivably vast, we are made of that world. The iron in our blood was forged before the earth existed, in the hearts of older, larger stars. The water in our cells fell on a young planet as the first rain. The carbon in every molecule of every living thing on Earth was processed, over billions of years, through the churning systems of a world that did not yet know what it was building. We are not separate from that story. We are its latest chapter. And it is a very good story. Rest now, if you are ready to rest. Let the image of that young world, orange glowing, rain-lashed, violent and strangely beautiful, drift at the edges of your thoughts. Let it settle into the deeper places, the places where time feels different and 4 billion years is not so unimaginable after all. We are just beginning. There is so much still to come. The first continents. The first chemistry that crosses the threshold into something we might dare call life. The long, slow transformation of the oceans, the sky, the very air. We will take it gently. We will take it one step at a time. For now, breathe. The earth has time. And tonight, so do you. There is something deeply human about wanting solid ground beneath your feet. We feel it instinctively. The relief of firm earth after water, the confidence of stone underfoot, the sense that the world will hold us. We build our cities on rock. We anchor our harbors to it. We bury our dead in it. Rock, for us, is permanence. Rock is the thing that stays. But rock, like everything else, had to begin somewhere. And in the early Archean, it was only just learning how. We left the young earth emerging from her first rains, the ocean still hot, still shallow, still more steam than sea in places. The crust that had formed above the cooling magma was thin and fragile, a skin of dark volcanic rock called basalt, constantly being fractured and remelted and reformed. There were no continents. There were no mountains. There was no land above the ocean's surface that would have lasted more than a geological eye blink before being swallowed back down into the heat below. The earth was restless in these years in a way she has never quite been since. Her interior was hotter, far hotter than it is today. The radioactive elements decaying in her mantle were younger then, and young radioactive elements decay faster, releasing more heat. The convection currents churning through the rock below were more vigorous, more chaotic, turning over the crust with a ferocity that makes modern plate tectonics look almost leisurely. She was not yet ready to build anything that would last. But she was getting there. The first permanent rock on Earth, the oldest rock, is something called tonalite transurmite granodiorite, a family of pale, coarse-grained igneous stones that geologists abbreviate, mercifully, to TTG. These are not glamorous names. They do not stir the imagination the way obsidian or granite might. But they are extraordinary things nonetheless, because they represent the first time that the chemistry of the Earth's interior produced something that could float. This is the key to understanding how continents form. It comes down to density. The basaltic oceanic crust, dark, heavy, iron-rich, is dense. When it is pushed down into the mantle, it sinks readily, melts, and recycles back into the deep. But TTG rock is different. It is lighter. When the wet basaltic crust is subducted and partially melted, the melt that rises back up through the mantle is less dense than what went down. It rises. It pools. It piles up. And because it is lighter than the mantle rock around it, it stays up. It does not sink back. It accumulates. Over millions of years, these accumulations of buoyant, pale rock grow. They thicken. They become cratons, the ancient, stable cores of what will eventually become continents. The oldest known craton material on Earth has been found in several places. The Akastic gneiss in what is now northwestern Canada dates to approximately 4 billion years ago, some of the oldest intact rock on the planet's surface. The Nouveau-Wadioutou greenstone belt in northern Quebec may be older still, with some researchers arguing for ages approaching 4.3 billion years, though this remains a subject of careful scientific debate. Hold those numbers gently. For billion years. The rock you could pick up and hold in your hand, in a remote stretch of the Canadian Shield, has been solid since before the oceans were full. It has survived every upheaval since every mountain-building event, every ice age, every extinction, every geological revolution. It has been pressed and cooked and folded, and it is still there, sitting at the surface, patient beyond all imagining. There is something quietly astonishing about that. In the early Archean, these cratons are small. Think of them not as continents yet but as islands. Scattered, isolated patches of solid ground rising just above the surface of a global, shallow sea. They are dark with volcanic rock at their edges, pale and grainy at their hearts. They are battered constantly by the continued meteorite impacts of the early solar system. They are lashed by storms in an atmosphere that has no ozone layer to soften the ultraviolet glare of the sun. They are not hospitable places. But they are places. That is new. For the first time, the Earth has geography. She has a surface that is not uniform, that has texture, variation, high and low. She has edges where rock meets water, where the chemistry of two very different environments mixes and reacts. Those edges will turn out to matter enormously. Beneath these early cratons, below the growing crust, the mantle continues its slow churning. And here we encounter one of the great questions of early Earth geology, one that scientists are still working to fully answer. How did plate tectonics begin? On the Earth we know today, the crust is divided into enormous plates, a dozen or so major ones, dozens of smaller ones that drift across the surface of the planet, driven by the convection of the mantle below. Where plates pull apart, magma wells up and new crust is born. Where plates collide, one is forced beneath the other, diving back down into the mantle in a process called subduction. Mountains rise where continents crunch together. Earthquakes rattle the fault lines between them. The whole system is elegant and interconnected, and responsible for almost every large-scale geological feature we can observe. But this system, at least in its modern form, did not exist in the early Archean. Or if it did, it worked very differently. The Earth's mantle then was hot enough that the crust above it may have behaved less like the rigid slabs of today and more like a thick, slowly deforming sheet, something geologists describe as a stagnant lid regime, or perhaps a more chaotic heat pipe model, where the interior vented its heat through numerous small volcanic conduits rather than organized plate boundaries. The truth, as best the science can reconstruct it, is somewhere in between, and it was probably changing over this long period, gradually transitioning toward something more like the plate tectonics we know today. What we can say with confidence is this: By the middle of the Archean, around 3 billion years ago, there is clear geological evidence of processes that look like subduction. Of crustal material being recycled. Of terrane's fragments of crust with distinct geological histories being welded together to form larger stable blocks. The continents were assembling. Slowly. Piece by piece. The way anything large and lasting is assembled. Picture it this way. The oceans of the early Archean are dark. Not blue, the sky is not yet the bright, oxygen-rich blue we know, and the sun appears through a permanent haze of volcanic aerosols as a pale, diffuse disk, perhaps reddish at the horizon. The water is warm, warmer than any ocean today, possibly as warm as 70 or 80 degrees Celsius in places near volcanic vents. It is also chemically extraordinary. Dissolved in those ancient seas is an inventory of elements and compounds that would be toxic to almost all of the life on Earth today. Iron, in enormous quantities. The oceans of the Archean are literally rust-colored in some regions, rich with dissolved ferrous iron that has nowhere to go, because there is no oxygen to react with it and precipitate it out. Silica. Sulfur compounds. The metals leached from the volcanic rock by the hot seawater circulating through cracks in the ocean floor. It is a rich broth. A chemically energetic broth. And chemistry, given time and energy, has a tendency to do surprising things. Along the mid-ocean ridges and around the submarine volcanoes, hydrothermal vents exhale superheated water into the cold of the deep sea, or what passes for cold, on a world this warm. These vents create steep chemical gradients, hot against cold, acidic against alkaline, reduced chemistry against oxidized. They create the conditions for reactions to happen spontaneously, reactions that build complexity from simplicity, that assemble larger molecules from smaller ones. We do not yet know, with certainty, where life on Earth began. The hydrothermal vent theory is one of the most compelling current hypotheses. The idea that life first flickered into existence in the warm, chemically rich environment of an alkaline hydrothermal vent, where proton gradients across mineral membranes could have powered the first primitive metabolisms. But there are other candidates, tidal pools, where evaporation concentrates organic molecules, the surfaces of clay minerals, where simple organic reactions can be catalyzed, even the subsurface rock itself, where liquid water circulates through cracks and carries with it the raw materials of chemistry. What we know for certain is this: somewhere in these Archean oceans, in this dark and ancient sea beneath a hazy sky, something happened. Something that changed everything. But we are not quite there yet. We will come to it. We will come to that moment with the care it deserves. For now, let us stay with the rock. With the slow, patient business of the Earth building her foundations. Because there is something worth dwelling on in the sheer scale of geological patience. The cratons that formed in the early Archean are still there, at the hearts of every continent. Under the ice of Greenland, under the grasslands of Central Africa, under the boreal forests of the Canadian Shield, under the red sands of the Australian outback, in all of these places and more, the ancient rock persists. Billions of years old. Pressed and deformed and intruded upon by 1,000 subsequent geological events, but fundamentally intact. The Earth does not throw away what works. She builds on it. She layers over it, welds new material to the edges, buries it under younger rock, but the old core remains. The oldest places on Earth are hidden in plain sight, under the skin of the continents, holding everything else up. There is a kind of comfort in that, perhaps. In the idea that the oldest things are still present. That the first ground is still somewhere beneath us, buried but real, unchanged in its essential nature. That the story does not discard its earlier chapters, it carries them forward, hidden in the structure of what comes next. The Earth remembers everything. Not in any conscious sense, not in any way that involves memory as we experience it, but in the physical sense, in the mineralogy of ancient rock, in the ratios of isotopes locked into crystals 4 billion years ago, in the orientation of magnetic minerals that record the direction of the magnetic field at the moment they cooled. She holds her own history, written in stone. And stone, it turns out, is very good at keeping secrets until the right questions are asked of it. So here is where we are, as the early Archean slowly gives way to the middle Archean, roughly 3.5 billion years ago. The oceans are full, not as deep as today, perhaps, but covering the majority of the surface. The first cratons float on the mantle, collecting at the edges, growing slowly as new material is added. Volcanoes are everywhere along the spreading zones where plates pull apart, above the subduction zones where cold crust dives back down, in great hotspot plumes where mantle material punches up through the crust from below. The sky is thick with carbon dioxide and methane, warm with a greenhouse effect that, paradoxically, is keeping the planet from freezing because the young sun, remember, is dimmer than it will eventually become, and without the greenhouse warming, the oceans would be ice. She is balanced on a knife's edge, the young Earth. Too little greenhouse gas and she freezes. Too much and the oceans boil. For billions of years she will walk that edge, sometimes nearly falling to one side, sometimes to the other, but always, so far, recovering. Always finding her way back to liquid water. To the one condition, above all others, that makes what comes next possible. And in the water, in the dark warm chemistry of those ancient seas, the first whisper of life is beginning. You are very old, in a way. Everything you are made of is very old. The calcium in the bones that hold you as you lie here, the iron moving through your blood, the water that makes up most of your weight, all of it has been on this planet for billions of years. All of it has cycled through the oceans and the rock and the atmosphere, over and over, in forms you would not recognize. You are the latest arrangement of very ancient material. And somewhere in those Archean oceans, in that dark, warm, chemically restless sea, the arrangement that eventually became you was just beginning to take its first tentative shape. Rest with that thought, if you like. We will follow the thread next time. There is a question that human beings have been asking, in one form or another, for as long as human beings have been capable of asking questions. Where did we come from? Not in the personal sense, not the family, the ancestry, the particular chain of people and events that led to any one of us. But in the deeper sense. The oldest sense. The sense that looks past all of that and asks, before any of it, before people, before animals, before anything alive at all, where did life come from? It is one of the great questions. Perhaps the great question. And the honest answer, the scientifically honest answer, is that we do not fully know. Not yet. The research is ongoing. The hypotheses are being tested. The ancient rocks are being interrogated with increasingly precise instruments, and every few years the picture sharpens a little more. But we know enough now to tell a story. Not a myth, a real story, grounded in chemistry and geology and the patient work of scientists who have spent their lives asking the rocks what they remember. Let us tell it gently. The Archean Ocean, 3.5 to 4 billion years ago, is not a quiet place. Above the surface, volcanic islands smolder. The atmosphere crackles with lightning, constant, brilliant, violent electrical storms driven by the heat differential between the warm ocean and the cooler upper atmosphere. Ultraviolet radiation from the sun pours down through an ozone-free sky, unfiltered and intense, striking the surface of the sea with an energy that would be lethal to almost anything alive today. Below the surface, it is a different world. The ocean is a filter. Even a few meters of water absorbs most of the ultraviolet radiation. Deeper down, the light fades entirely, and the darkness is complete, and the only illumination comes from the faint glow of hydrothermal vents, cracks in the ocean floor where superheated water, laden with dissolved minerals, pours out into the cold of the deep. It is in this world, dark, warm, chemically rich, electric, that something begins. Before we can talk about life, we need to talk about chemistry. Because life, at its most fundamental level, is chemistry. Extraordinarily complex, self-replicating, energy-consuming chemistry, but chemistry nonetheless. And the chemistry that makes life possible had to assemble itself, step by step, from the simpler molecules that were abundant in the early Archean world. The building blocks were there. That much we know. The early Earth's atmosphere, rich in carbon dioxide, nitrogen, methane, ammonia, hydrogen sulfide, was a reservoir of the raw materials that life is built from. In a famous experiment in 1953, the chemists Stanley Miller and Harold Urey sealed these gases into a flask with liquid water and ran electrical sparks through the mixture, simulating lightning. Within a week, they found amino acids in the water. the basic structural units of proteins, assembling themselves spontaneously from simple gases and electricity. The building blocks, it seems, want to form. Given the right ingredients and a source of energy, the universe has a tendency to assemble complexity. The question is not whether the ingredients were present in the early Archean. They were. The question is how the step was made, the vast, extraordinary step from chemistry to life. The hydrothermal vent hypothesis is perhaps the most compelling current answer to that question. Let us walk through it slowly, because it repays attention. Deep on the ocean floor of the early Archean, there are places where seawater percolates down through cracks in the basaltic crust and comes into contact with the hot rock below. As it heats, it dissolves minerals from the rock's silica, iron, sulfur compounds, hydrogen. It becomes chemically transformed. And then it rises back up, forced back toward the surface by the pressure of the hot rock around it, emerging through vents on the seafloor as superheated fluid. There are two kinds of hydrothermal vents, and they are very different from each other. The black smokers familiar from television documentaries, dramatic and beautiful, vent extremely hot, acidic, mineral-rich water that precipitates dark clouds of iron and sulfur particles as it hits the cold of the deep ocean. They are spectacular, and they host remarkable ecosystems today. But the vents that may have given rise to life are the white smokers, gentler, cooler, alkaline rather than acidic, and built from a different chemistry entirely. The most famous of these is the Lost City hydrothermal field in the Atlantic Ocean, discovered in the year 2000, a forest of towering white carbonate chimneys, some as tall as 60 meters, exhaling warm, alkaline fluid rich in hydrogen. These alkaline vents are interesting for a very specific reason. The fluid coming out of them is alkaline. The ancient ocean around them was slightly acidic. This means there is a natural proton gradient across the wall of the vent, a difference in acidity, in the concentration of hydrogen ions, between the inside of the vent and the outside. And proton gradients, it turns out, are exactly what life uses to generate energy. Every living cell on Earth today, from the simplest bacterium to the most complex human neuron, uses a mechanism called the proton gradient to power itself. Hydrogen ions are pumped across a membrane. They flow back through tiny molecular turbines. Those turbines generate the chemical energy currency of life, a molecule called ATP. This process, called chemiosmosis, is so fundamental and so universal that it appears to have been present in the very earliest life. It is arguably the deepest common feature shared by all living things. And at an alkaline hydrothermal vent, it happens naturally. For free. Without any biological machinery to drive it. The geology provides the gradient. The chemistry provides the flow. The hypothesis, developed most fully by the biochemist Nick Lane and others, is elegant and compelling. Life did not need to invent the proton gradient. It inherited it. The first protocells simply learned to harness and eventually to replicate internally a gradient that the rocks themselves were already providing. But chemistry, however rich, is not yet life. There is a threshold. A crossing. The moment at which a collection of self-assembling molecules becomes something more, something that can make copies of itself, that can capture energy and use it to maintain its own organization against the constant pressure of entropy that seeks to dissolve all order back into chaos. That threshold is the origin of life. And it remains, honestly, the most mysterious single event in the history of this planet. What we can say is this. At some point in the Archean, the geological and isotopic evidence suggests it was very early, perhaps as far back as 3.7 or even 4 billion years ago. Something capable of leaving a chemical signature of life existed on Earth. Microfossils, tiny, cell-shaped structures preserved in ancient chert, a hard silica-rich rock, have been found in formations dating to approximately 3.5 billion years in the Pilbara region of Western Australia. The carbon isotope ratios in even older rocks whisper of biological processes, of organisms that were already selecting lighter carbon atoms in the characteristic way that life does. Life, it seems, did not take long. On a geological timescale, almost as soon as the oceans were cool enough to hold liquid water, life appeared in them. Which tells us something remarkable. Life, under the right conditions, is not an improbable accident. It is something close to an inevitability. The earliest life was nothing like us. It was nothing like anything we can see with the naked eye. It had no nucleus, no complex internal structures, no differentiated cells. It was prokaryotic, the simplest possible form of cellular life. A membrane surrounding a small volume of chemistry, containing genetic information encoded in molecules of RNA or DNA, capable of carrying out a handful of metabolic reactions, capable of dividing and producing copies of itself. That is all. Just that. And yet just that is everything. Just that is the difference between a planet with life and a planet without it. Just that is the seed of everything that will follow, every bacterium, every plant, every animal, every thought that has ever been thought on this world. The distance between no life and the simplest possible life is, arguably, the greatest distance there is. In the darkness of the Archean Ocean, these first organisms live lives of extraordinary chemical intimacy with their environment. They do not breathe oxygen, there is no oxygen to breathe. Instead, they are what we call chemolithotrophs. They feed on chemical energy, drawing power from reactions between hydrogen and carbon dioxide, or between sulfur compounds, or from the gradient of the hydrothermal vents. They are, in a sense, eating rock. Eating the chemical disequilibrium of the Earth itself. They have no eyes, no senses, no anything that we would recognize as experience. They simply persist. They metabolize. They divide. They are, in the most minimal possible sense, alive. And yet they are already changing the world. As these first organisms metabolize, they process the chemistry of the ocean around them. They take in molecules and release others. Their waste products accumulate. Their bodies, when they die, sink to the ocean floor and become part of the sediment. They are so small, individually, as to be invisible, but there are so many of them, and they have so much time, that their collective impact on the chemistry of the oceans and atmosphere will turn out to be staggering. We will come to that. We will come to the greatest pollution event in Earth's history, and to the revolution it caused. But that is still a billion years away. For now, in these dark and ancient waters, life is simply finding its feet. Figuring out what it is. What it can do. What it means to persist. There is a particular kind of silence in the deep ocean. Not the silence of absence, because the deep ocean is full of chemical reactions, of thermal convection, of the creaking and settling of rock under pressure. But the silence of a place where sound travels differently, where the ordinary categories of quiet and loud simply do not apply. In that silence, in that darkness, in that warm chemical broth, the first living things divided. And divided again. And spread, slowly, through the hydrothermal vent systems, through the cracks in the rock, through the shallow margins of the volcanic islands above. Life, once it began, did not stay in one place. It never has. Imagine the Earth from space, 3.5 billion years ago. She looks, from a great distance, not entirely unlike how she looks today, a sphere, partly covered in cloud, with dark oceans and the dark masses of the first small continents. But she is quieter than she will become. There is no green on those continents, no life has yet colonized the land. There is no blue in the sky, no oxygen, no scattered blue light. The atmosphere is brownish, reddish, hazy with methane. And in the oceans, invisible, microscopic, unimaginably numerous life. Teeming in the warm shallows around the volcanic islands. Clustered around the hydrothermal vents on the deep ocean floor. Drifting in the surface waters, where some have found a way to capture a little of the sun's light and use it as a power source. That last innovation, photosynthesis, the ability to harvest sunlight directly, is still developing in this period. The earliest photosynthesis was not the kind we are most familiar with, the kind that releases oxygen. It was a more primitive version, using hydrogen sulfide rather than water, releasing sulfur rather than oxygen. But it was a beginning. The first time life looked upward, toward the light, and found a way to drink it. Let the image settle for a moment. A dark ocean. Warm. Ancient. And in it, the first living things are so small as to be invisible, so simple as to seem almost like chemistry rather than biology, and yet unmistakably alive. Metabolizing. Dividing. Adapting. Already, in their small and patient way, beginning to change the world. This is perhaps the most important thing that has ever happened. And it happened in the dark, without witness, without fanfare, in a place that no human eye has ever seen and no human foot has ever trod. Life does not announce itself. It simply begins, quietly, and then gets on with the business of becoming. You are the product of an unbroken chain. Every organism that has ever lived on this planet is connected through the mechanism of reproduction, through the sharing and modification of genetic information in a single, unbroken lineage that stretches back to those first cells in the Archean Ocean. There have been no gaps. Not once, in 4 billion years, has the thread been broken. You are continuous with the first life on Earth. That is not a metaphor. It is a biological fact. The oceans are dark. The world is young. And something, in the warm chemical margins of an ancient sea, has just made the most extraordinary decision the universe has ever witnessed. To be alive? Let that carry you, now, into whatever comes next. Whether that is sleep, or the soft drift of half-waking, or simply the quiet pleasure of a mind released from the urgency of the day. You come from very far away. And you are here. Rest. Life, once it finds its footing, does not stay still. This is perhaps the most fundamental thing about it, more fundamental, even, than the chemistry, more fundamental than the genetics. Life moves. Life spreads. Life finds the edges of what is possible and then, patiently, persistently, without intention but with an almost inexorable momentum, it pushes past them. In the early Archean, the first organisms were confined, most likely, to the warm chemical margins where they had arisen, the hydrothermal vents, the shallow shores of volcanic islands, the sunlit surface waters of a warm, iron-rich sea. They were small. They were simple. They were, individually, insignificant. But life is never really individual. Not for long. Life is, almost from the very beginning, collective. And it is in the collective that its true power emerges. Allow yourself to picture a shoreline. Not a shoreline you know, not sand and surf and the smell of salt and seaweed. This is an Archean shoreline, 3.5 billion years ago. The rock is dark basalt, still warm to the touch from the volcanic activity nearby. The sea is shallow here, shallow enough for light to reach the bottom, warm enough to feel almost like a bath. The sky above is not blue, it is a kind of pale amber orange, filtered through the methane haze of an atmosphere without oxygen. The sun, somewhat dimmer than we know it, hangs in a sky that has never been seen by eyes, because eyes have not yet been invented. And at the waterline, at the exact meeting place of rock and sea, of light and chemistry, there is something. A thin film. A layer so subtle you might mistake it for a stain on the rock, a discoloration, a trick of the light. It is greenish, perhaps, or brownish, or somewhere between the two. It does not move. It does not make a sound. It does not, in any obvious way, do anything at all. But it is alive. It is a microbial matter community of microscopic organisms, layered together in a thin film of their own making, collectively metabolizing, collectively responding to the chemistry around them, collectively beginning to reshape the environment they inhabit. It is the first visible sign of life on Earth. Microbial mats are extraordinary things. They are not organisms in themselves, they are communities, ecosystems compressed into a layer sometimes no thicker than a piece of paper. Different organisms occupy different layers, each adapted to the conditions at their particular depth, the uppermost layer exposed to sunlight and the chemistry of the open water, the middle layers living in the metabolic output of those above them, the deepest layers working in near-complete darkness, processing what falls down from above. They are, in miniature, a complete ecology. The first ecology. And they are more robust, more ancient, more persistent than almost anything else that has ever lived. Microbial mats exist today in hot springs, in hypersaline lakes, in Antarctic ice. They have survived every mass extinction. They have outlasted the dinosaurs, the trilobites, the great fern forests of the Carboniferous. They were here 3.5 billion years ago, and they are here still, going about the same quiet business, largely indifferent to everything that has happened on the surface above them. But the microbial mat is a beginning. What it eventually builds is something more lasting, more visible, more wonderful. The stromatolite. The word comes from the Greek stroma, meaning layer, and lithos, meaning stone. A layered stone. And that is, in its plainest description, exactly what a stromatolite is, a structure built by microbial mats, layer by layer, over thousands of years, as the organisms trap and bind sediment from the water around them and cement it into place with the minerals they precipitate from their own chemistry. They grow slowly. Extraordinarily slowly. A centimeter a century, in some cases. They build domes and columns and sheets, their shapes determined by the currents of the water around them, by the angle of the sunlight, by the chemistry of the local sea. They look, in photographs, like mushrooms made of stone. Or like the heads of enormous ancient cauliflowers, clustered on the seafloor. Or, in cross-section, like the rings of a tree layer upon layer, each one representing years of patient, microscopic life. The oldest stromatolites yet found come from the Dresser Formation in the Pilbara region of Western Australia, those same ancient rocks we mentioned before. They date to approximately 3.5 billion years ago. They are not small, solitary structures. They are extensive reef-like, covering areas of ancient seafloor, built up over millions of years by uncountable generations of microbial communities. They are the first reefs. The first structures built by life that were large enough to change the physical environment around them. The first moment in which the organisms on this planet were not merely passengers in the world but architects of it. It is a role that life has never relinquished since. But the stromatolites are more than monuments. They are engines. The organisms that build them, the dominant architects of the stromatolite reefs, are cyanobacteria. And cyanobacteria are doing something that, in the context of the early Archean, is genuinely revolutionary. Something that will change the Earth more profoundly than any geological event since the cooling of the magma ocean. They are performing oxygenic photosynthesis. Let us slow down here, because this matters enormously. The earlier photosynthesizers we mentioned, the ones working in the deep sea, using hydrogen sulfide, were capturing sunlight but releasing sulfur as their waste product. Cyanobacteria have developed a more powerful trick. They split water. They use the energy of sunlight to break apart the water molecule HO, extracting the hydrogen to build sugars and organic compounds, and releasing the leftover oxygen into the surrounding environment. Oxygen. As waste. To a cyanobacterium, oxygen is a byproduct. An exhaust. Something to be discarded. But to the chemistry of the early Earth and, eventually, to the history of everything that follows, it is the most consequential substance ever produced by any living thing. In the shallow, sunlit waters of the Archean, the cyanobacterial mats are busily photosynthesizing. Every hour, every day, every year, releasing tiny bubbles of oxygen into the water around them. For now, in the early and middle Archean, almost all of that oxygen is instantly absorbed. The ocean is full of dissolved iron. Remember that rusty, ferrous iron that has been accumulating for hundreds of millions of years with nowhere to react. The oxygen from the cyanobacteria finds it immediately. Iron plus oxygen forms iron oxide rust and precipitates out of the water, sinking to the ocean floor in a slow, steady rain of reddish sediment. This process, the banded iron formations, creates some of the most visually striking rocks on Earth. Layers of red and gray, alternating in bands as regular as a barcode, stretching across ancient formations in Australia, Canada, South Africa, Brazil. When you look at a banded iron formation, you are looking at the exhaust product of billions of years of microbial life. You are looking at the oxygen that was produced but immediately consumed, captured, neutralized, turned to stone. The cyanobacteria are running a race against the chemistry of the ocean. And for hundreds of millions of years, the ocean is winning. All that oxygen, produced so patiently, so relentlessly swallowed up, turned to rust. But the iron supply is not infinite. And the cyanobacteria are tireless. Stand for a moment in that shallow Archean sea, if you can hold the image. The water is warm. It is clear near the surface, catching the diffuse amber light of a hazy sun, deepening to green and then to dark as the depth increases. The seafloor in the shallows is covered in the rounded domes of stromatolites, gray and brown and muted, but built with a precision and patience that no human mason has ever matched. Between the domes, the sediment is reddish with precipitated iron oxide. And from the surface of the mats, from the uppermost cyanobacterial layer where the sunlight reaches, tiny bubbles are rising. So small as to be almost invisible. Rising slowly through the warm water, reaching the surface, joining the atmosphere. These are the first bubbles of free oxygen that this planet has ever known. They are produced by organisms that have no awareness of what they are doing, no knowledge of the revolution they are building, no concept of the world they are in the process of creating. They are simply doing what their chemistry allows them to do. They do not know. And yet, the oxygen will accumulate. Slowly, so slowly that 200 million years will pass before the concentration rises to a level that can even be measured in the rock record. And then, about 2.4 billion years ago, just at the end of the Archean, just as we are beginning to approach the next great chapter of Earth's story, it will break through. The iron reserves in the ocean will be exhausted. The oxygen will have nowhere left to go. And it will begin, for the first time, to accumulate in the atmosphere. This event, the Great Oxidation Event, as it is called, is coming. We will meet it properly in time. But it is worth knowing now, as we watch the stromatolites build their quiet reefs in the warm shallows of the Archean Sea, that the fuse is already lit. Has been lit, in fact, for hundreds of millions of years. The cyanobacteria do not know they are changing the world. They are just living. Just doing what they do. It will be enough. There is something I want you to carry from this segment. Something that the stromatolites, in their patient, wordless way, seem to teach. Great change does not always announce itself. It does not always arrive with drama and upheaval, with the impact of a comet or the eruption of a supervolcano. Sometimes, often, perhaps the most profound transformations happen slowly, quietly, in the margins, carried out by small things working steadily over enormous spans of time. The cyanobacteria did not storm the world. They did not conquer it. They simply inhabited it, one generation at a time, doing the thing their chemistry was built to do. And the cumulative weight of all those quiet generations, all those tiny bubbles rising through warm water, was enough to change the atmosphere of an entire planet. The small and patient things matter. They always have. In Western Australia today, in a shallow, hypersaline lagoon called Shark Bay, you can still find living stromatolites. They grow in the warm, salty water at the edge of the sea, looking almost exactly as they have for 3.5 billion years. Tourists come to see them. They stand on the boardwalk and look at the rounded shapes in the shallow water, and sometimes they are not sure what they are looking at. They seem so plain, so unimpressive, so much like ordinary rocks. They are not ordinary rocks. They are the oldest living structures on Earth. They are, in the most literal sense, our ancestors. Not metaphorically, biologically. The chemistry that powers every cell in your body is descended from the chemistry that those mats were running in the Archean Sea. The mechanism by which your cells generate energy, the way your blood carries oxygen, the very oxygen you breathe, all of it traces back, through an unbroken chain of life and chemistry and evolution, to the humble cyanobacterium and its quiet, revolutionary bubble. Soften here. The pace is very slow now. We are deep in the segment. The Archean night, and there were nights, even then, because the Earth was already spinning, though faster than today, with days perhaps only 12 or 15 hours long. The Archean night was dark in a way we have no modern frame for. No light from any settlement. No glow on any horizon. Just the darkness of a world without eyes, and the quiet hiss of the sea against the warm, wet stone of the first shores. And in the water, the mats were still metabolizing. Still dividing. Still building, layer by layer, the slow patient architecture of the first reefs. Under a sky full of stars that no one was watching yet, in water that no one had yet tasted, the work went on. It always goes on. That is what life does. That is what it has always done. It goes on. If you are still awake, if you are still with me at the edge of sleep, then breathe. The air coming into your lungs right now is 21% oxygen. Every molecule of it was produced by a photosynthesizing organism, a plant, an alga, a cyanobacterium. Every breath you take is a gift from billions of years of patient, microscopic life. You are breathing the Archean. It has taken 4 billion years to get to this breath. It was worth the wait. Everything we have talked about so far has happened at the surface. The rains filling the first oceans. The craton rock slowly accumulating. The microbial mat spreading across the shallow seafloor. All of that extraordinary, consequential activity has been a surface story. A skin-deep story, in the most literal sense. But the Earth is not just a surface. She is, above all else, an interior. A vast, hot, churning interior that makes everything at the surface possible, that drives it, that shapes it, that has been working without pause since before the first drop of rain fell. The surface of the Earth, with all its drama and complexity, is in many ways simply the visible expression of forces moving far below. Tonight we go down. Imagine pressing your hand flat against the ground. Feeling the solidity of it, the reassuring, unyielding hardness of rock. Now imagine that the rock beneath your hand is only the outermost layer of a structure that extends downward for nearly 6,500 kilometers. Imagine that just 30 kilometers below your palm, no further than a short drive down a motorway, the rock is under pressures that would instantly crush any human-made vessel. And that 100 kilometers below, it is beginning to behave less like a solid and more like an extraordinarily viscous liquid. And that deeper still, at depths of hundreds of kilometers, the rock flows slowly, over millions of years, but flows nonetheless, driven by the heat bleeding upward from the core at the very center. The Earth is not a cold, dead rock with a thin skin of activity on top. She is alive with heat. She is a heat engine of staggering scale and patience, converting the energy of her own formation and the energy of radioactive decay into the slow circulation of her interior, and that circulation, expressed at the surface as volcanism and tectonics and mountain building, is the engine of almost everything we have been watching. In the Archean, this engine runs hotter than it does today. The difference matters. The mantle of the early Earth, the thick layer of rock between the crust above and the core below, making up about 84% of the planet's volume, is perhaps 200 to 300 degrees Celsius hotter than the modern mantle. That may not sound like much against the backdrop of temperatures that run into the thousands of degrees in the deep interior. But in terms of what it means for the behavior of the rock, for the vigor of convection, for the pace and character of geological activity at the surface, it is enormous. Hot mantle rock rises. Cooler rock sinks. This convection is the same principle that moves the water in a heated pot, the same principle that moves air in a warm room. But in the mantle, the scale is continental and the timescale is geological. A single convection cell in the Archean mantle might be thousands of kilometers across and take tens of millions of years to complete one full turn. And yet it turns. Slowly, majestically, driven by the heat it cannot help but shed. At the very center of the Earth, the core. It is divided into two parts. The inner core solid, or at least behaving like a solid under the extraordinary pressures at the center of the planet, is a ball of iron and nickel roughly the size of the moon. Around it, the outer core, liquid iron and nickel, churning in complex flows driven by the heat bleeding outward and by the Coriolis forces of the Earth's rotation. This churning liquid metal is the source of the magnetic field we discussed in the first segment, the dynamo that wraps the Earth in its protective electromagnetic embrace. But in the Archean, the details of how this dynamo operated are still a matter of scientific investigation. The inner core, as best we can determine, was smaller, then perhaps absent altogether in the earliest Archean, the entire core still liquid, before the slow cooling of billions of years had begun to solidify its center. The magnetic field existed. The geological record of magnetized minerals in ancient rocks confirms it went back at least to 3.5 billion years ago, and likely further. But it may have been less stable, less regular, more prone to reversal and fluctuation than the field of today. Think of it as a shield still finding its shape. The heat of the Archean mantle expresses itself at the surface in a particularly dramatic way, the komatiite lava. Komatiites are a type of volcanic rock that exists in abundance in Archean terrains and is almost entirely absent from younger geological formations. This tells us something important. Komatiites require extraordinarily high mantle temperatures to form, temperatures of perhaps 1500 degrees Celsius or more, far above what the modern mantle reaches. They flow when erupted not as the thick, slow lava of a modern shield volcano, but as something closer to a liquid thin, fast-moving, spreading across the landscape in sheets. Imagine a lava flow that moves not like treacle, but like water, spreading rapidly, filling valleys, covering everything. Komatiite eruptions in the Archean would have been among the most spectacular geological events on a planet already defined by geological spectacle. They are, in a sense, the fingerprints of a hotter world. Wherever geologists find komatiites in the rock record today, they know they are reading a page from the deep past, from a time when the Earth ran hotter and faster and more violently than anything the modern planet can produce. Beneath the surface of the Archean Ocean, the mid-ocean ridge system is operating, though, as we discussed, in a form that may be more chaotic, less organized into the clean linear ridge and trench geometry of today. Where the plates pull apart, the mantle wells up to fill the gap, decompressing as it rises, melting as the pressure drops, emerging as basaltic lava on the ocean floor. This process, seafloor spreading, is both a geological and a chemical process. The fresh basalt reacts with the seawater. Elements are exchanged. The ocean is constantly, chemically negotiating with the rock beneath it, absorbing some elements and releasing others. The hydrothermal circulation we discussed in the context of life's origin is one expression of this negotiated seawater circulating through hot rock, being transformed, venting back into the ocean. The ocean and the seafloor are not separate things. They are one continuous system, endlessly exchanging chemistry, endlessly shaping each other. And the mantle, below it all, is the heat source that drives everything. There is a concept in geology called the Wilson cycle, the idea that ocean basins open and close over geological time, that continents drift apart and eventually collide again, that the geography of the Earth's surface is not fixed but is perpetually rearranging itself on a timescale of hundreds of millions of years. The modern version of this cycle, fully developed plate tectonics, is the expression of the mantle's heat finding its way to the surface. In the Archean, the Wilson cycle is not yet operating in its modern form. The mantle is too hot. The lithosphere, the rigid outer layer that includes the crust and the uppermost mantle, is thinner, weaker, less capable of sustaining the rigid plate behavior of today. Some geologists argue for a stagnant lid regime early on, transitioning gradually to something more mobile. Others point to evidence of early subduction in rocks as old as 3.5 billion years. The truth, as the rocks tell it, seems to be a gradual transition, a slow cooling, a slow thickening of the lithosphere, a slow organization of the chaotic early heat venting into the more structured, more elegant system of today. Not a sudden switch, but a billion-year conversation between a cooling interior and a thickening skin. Down, still deeper. Past the mantle transition zone at about 660 kilometers depth, where the crystal structure of the minerals changes under the pressure, where the rock above behaves differently from the rock below. Past the lower mantle, where pressures are so extreme that familiar minerals become unrecognizable, compressed into dense crystal forms that have no surface equivalent. To the core mantle boundary, nearly 2,900 kilometers below the surface. A place of extraordinary complexity and drama, where the liquid iron of the outer core meets the solid silicate rock of the mantle in a boundary that is not smooth but turbulent, where vast plumes of hot rock, heated by contact with the even hotter core, detach and begin their long, slow rise to the surface. These are the mantle plumes, columns of exceptionally hot rock rising through the mantle like slow-motion fountains, eventually punching through the lithosphere above as hotspots. Iceland, sitting on the mid-Atlantic ridge, is a hotspot. The mantle plume there is so vigorous that it builds a volcanic island above the ridge. Hawaii is another chain of volcanic islands tracking the movement of the Pacific plate over a stationary hotspot below. In the Archean, mantle plumes were more numerous, more vigorous, more central to the geological story. The hotter mantle produced more of them, and more powerful ones. Some researchers believe that the large igneous provinces and the vast outpourings of lava that periodically resurface significant portions of the crust were even more frequent in the Archean than they are today. The Earth was venting her heat through every channel available. The crust above was the release valve, and it ran hot. There is a particular quality to thinking about the deep interior of the Earth. It is, in some ways, more alien than thinking about deep space, because space, at least, we can observe directly. We can see the stars. We can measure their light. We can, with the right instruments, learn their composition and temperature and age. The deep interior of the Earth is invisible to us. We have never sampled it. The deepest hole ever drilled, the Kola superdeep borehole in Russia, a project that took decades and pushed Soviet engineering to its absolute limits, reached just over 12 kilometers before it had to stop, defeated by heat and pressure. 12 kilometers. Not even halfway to the base of the crust. Everything we know about the deep Earth comes from seismology, from listening to the echoes of earthquakes as they travel through the planet's interior, bending and reflecting and changing speed as they pass through different materials. The interior of the Earth has been mapped not with cameras or drills, but with sound. And yet the picture is astonishingly detailed. We know the depth of the core mantle boundary to within a few kilometers. We know the temperature of the inner core boundary to within a few hundred degrees. We can trace the paths of mantle plumes, can map the subducted slabs of old ocean crust that have sunk into the deep mantle and still sit there, cold and dense, thousands of kilometers below where they began. The Earth keeps her deepest secrets, but she is not entirely silent about them. Come back up, now. Rise slowly through the dark rock of the lower mantle, through the transition zone, through the upper mantle with its slowly circulating currents of hot rock. Past the root of a crater, a deep, cold, buoyant keel of ancient lithosphere extending hundreds of kilometers down, stabilizing the continent above it like the keel of a ship. Up through the crust, through the 30 kilometers of rock that separate the deep Earth from the surface world. And emerge into the Archean Ocean. The warm, shallow, iron-rich sea. The stromatolite reefs building their quiet columns in the shallows. The volcanic islands smoldering in the amber haze. The first thin cratons drifting slowly across the surface, driven by the convection of the mantle below. Everything at the surface is connected to everything below. The volcanism that built the first islands came from the mantle. The minerals that fed the first organisms were dissolved from rock by seawater circulating through the hydrothermal systems driven by mantle heat. The cratons that float above were partly built from mantle rock, differentiated and risen. The magnetic field that shields all of it from the solar wind is generated by the churning of the liquid outer core. There is no surface without depth. There is no story of the outside without the story of the inside. The Earth is one system, deep to surface, and in the Archean that system ran hotter and faster and more violently than at any time since. She was young, and full of heat, and working very hard. Think of the ground beneath you as you lie here. Through the floor, through the foundations, through the soil and the bedrock down through kilometers of rock you will never see and could never reach. The heat is there. Faint now, distant, much cooled from those early days. But present. The Earth is still warm at her center. Still generating a magnetic field. Still convecting, still venting heat through volcanoes, still rearranging her surface in the slow waltz of tectonic plates. She is not finished. She will not be finished for billions of years yet. She is a planet still in the middle of her story. And so, resting here, at the surface of her cushioned by the thin film of air she holds around herself, warmed by the sun she orbits, so are you. Rest in that. Rest in the warmth of a world that is still, after all this time, quietly burning. Everything we have told you so far, the magma oceans, the first rains, the growing cratons, the microbial mats, the deep churning of the mantle, none of it was witnessed. There were no observers. There were no notes taken. There were no photographs, no recordings, no accounts passed down through any chain of memory. For most of the Archean, there was not even anything alive that was complex enough to be affected by its surroundings in a way that left a meaningful impression. The Archean happened, and it passed, and it left behind only one thing, the rock. And from the rock, patiently, carefully, with instruments of extraordinary precision and minds trained to read a language written in mineral and isotope and crystal structure, scientists have reconstructed a world. That reconstruction is, in its own way, one of the most remarkable things human beings have ever done. To read rock is to read time. Not metaphorically, literally. The minerals that crystallize from cooling magma, the sediments that settle on ancient seafloors, the metamorphic rocks pressed and cooked by the weight of mountains above them, all of these carry within their structure a record of the conditions under which they formed. Temperature, pressure, chemical environment, the presence or absence of water, the composition of the atmosphere. Even, in some cases, the direction of the magnetic field at the moment the rock solidified. The Earth has been keeping a diary. It is not written in any language designed for human reading. But it is legible, to those who know how to look. The most fundamental tool for reading deep time is radiometric dating. It works because certain atoms are unstable, they are radioactive, and they decay, spontaneously and at a perfectly predictable rate, from one element into another. Uranium decays to lead. Potassium decays to argon. Rubidium decays to strontium. The rate of decay for each of these pairs is known with extraordinary precision, measured not in years but in half-lives that span billions of years. When a mineral crystallizes from molten rock, it locks in a certain ratio of parent to daughter atoms, the radioactive element and the element it decays into. From the moment of crystallization, the clock starts. The parent decays into the daughter at its known rate. And when a geologist, billions of years later, measures the ratio of parent to daughter atoms in that mineral, the mathematics tells them, with remarkable accuracy, how long ago the crystal formed. This is how we know the acoustic gneiss is 4 billion years old. This is how we know the age of the moon rocks brought back by the Apollo missions. This is how we know, with confidence, the age of the Earth itself. Time, crystallized in mineral. Readable, if you ask the right questions. But age alone is not the whole story. The rocks of the Archean are not just timestamps, they are environments. Each rock type carries within its composition and texture a detailed account of the conditions under which it formed. The zircon crystal deserves particular attention here. Zircon is a mineral of almost magical durability, a tiny, hard crystal of zirconium silicate that resists weathering, resists heat, resists the chemical assault of billions of years of geological processes. When other rocks are metamorphosed and recrystallized and worn away to sediment and carried away by ancient rivers, the zircons survive. They are concentrated in sediments, buried, lithified into new rock, and they carry with them, intact, the chemical memory of the magma that originally formed them. The oldest known material on Earth is not a rock. It is a zircon crystal. Found in the Jack Hills of Western Australia, it dates to 4.4 billion years ago, just 100 million years after the formation of the Earth itself. This crystal was already old when the Archean began. It has survived, essentially unchanged at the atomic scale, through everything that has happened since. Inside that crystal, in the ratios of oxygen isotopes locked into its structure, is information about the temperature of the water in which the magma that formed it was quenched. And that information tells us something extraordinary. At 4.4 billion years ago, liquid water was already present on the surface of the Earth. The oceans are older than almost anyone expected. A single crystal, the size of a grain of sand, rewriting the history of the world. The isotopes deserve their own moment of appreciation, because they are among the most powerful tools in the geologist's kit. An element is defined by the number of protons in its nucleus. Carbon is carbon because it has 6 protons. Oxygen is oxygen because it has 8. But the number of neutrons can vary, and atoms of the same element with different numbers of neutrons are called isotopes. They behave almost identically in chemical reactions, but they have slightly different masses, and that slight difference in mass means they are sorted, very slightly, by physical processes. Water made with the heavier oxygen isotope oxygen-18 evaporates a little less readily than water made with the lighter oxygen-16. So in cold periods, when more water is locked up in ice, which preferentially contains the lighter isotope, the ocean becomes enriched in the heavier one. By measuring the ratio of oxygen isotopes in ancient carbonate shells or in ancient ice cores, scientists can reconstruct the temperature of the ocean or the atmosphere at the time those shells or that ice formed. In the Archean, where there are no shells and no ice cores, the isotopic signals come from other sources, from the minerals in ancient cherts, from the carbon isotope ratios in organic rich sediments. The carbon isotopes, in particular, carry the signature of life, Photosynthesizing organisms preferentially take up the lighter carbon, 12 over the heavier carbon, 13, and this preference leaves a distinctive chemical fingerprint in the sediments where organic matter has accumulated. It is one of the key lines of evidence that life existed as far back as 3.7 or even 4 billion years ago. Not a fossil, not a visible trace, just a number. A ratio of isotopes, slightly off from what non-biological chemistry would produce, whispering across 4 billion years, something was alive here. The greenstone belts of the Archean are among the most scientifically valuable terrains on Earth. They are preserved remnants of ancient oceanic and volcanic crust sequences of volcanic and sedimentary rock, folded and metamorphosed but still recognizable, that date back as far as 3.8 billion years. The name comes from the green minerals chlorite, epidote, actinolite that form when basaltic rock is metamorphosed at relatively low temperatures and pressures. They give these ancient terrains their characteristic color, a deep greenish gray, visible in the exposed rock faces of the Canadian Shield, the Karpval Craton of South Africa, the Yilgarn Craton of Western Australia. Inside the greenstone belts, geologists find pillow lavas, rounded, lobate shapes formed when lava erupts underwater and the outer surface quenches instantly in the cold ocean, forming a glassy skin around a still liquid interior. Each pillow a frozen moment of eruption. Each one a confirmation that the rock was formed on an ancient seafloor, beneath an ancient ocean. They find banded iron formations, those distinctive rust and gray stripes we talked about, the accumulated exhaust product of billions of years of microbial photosynthesis. They find hard, fine-grained silica rocks within which, under a microscope, the outlines of some of the oldest microfossils on Earth can sometimes be made out. Tiny, cell-shaped structures, preserved in silica like insects in amber, carrying their shape across 3.5 billion years. And they find komatiites, those ultra-hot volcanic rocks that told us the Archean mantle was far hotter than today's. Read together, the greenstone belts are a library. Ancient, difficult, written in a language that takes years to learn. But a library nonetheless. There is a particular satisfaction in this kind of reading. In holding a piece of 4-billion-year-old rock and knowing, not guessing, not imagining, but knowing, through the precise language of geochemistry, something true about the world in which that rock was made. The scientists who do this work have a patience that is, perhaps, geological in its own way. They spend their careers on single rock formations. They argue, carefully and thoroughly, about the interpretation of isotope ratios that differ by fractions of a percent. They travel to the most remote corners of the Canadian Shield and the Western Australian outback, where the ancient rocks are still exposed at the surface, because in most of the world the Archean crust is buried under billions of years of younger geology. They are, in a real sense, archaeologists of deep time. Except that their artifacts are not pottery or bone but mineral and crystal, and their timescales are not centuries or millennia but billions of years. And what they have recovered piece by piece, isotope ratio by isotope ratio, microfossil by microfossil, is nothing less than the biography of the Earth. I want to tell you about one more technique, because it is perhaps the most evocative. Paleomagnetism. When certain minerals cool through a temperature called the Curie point, the magnetic domains within them align themselves with the Earth's magnetic field at that moment like tiny compass needles, frozen in place as the rock solidifies. And they stay frozen. For billions of years, as the rock is carried by tectonic plates across the surface of the Earth, those compass needles remember the direction and inclination of the magnetic field at the moment they cooled. By measuring the paleomagnetic signal in ancient rocks, the direction those frozen compass needles point, geologists can determine the latitude at which the rock formed. Not the longitude, magnetic fields don't preserve that, but the latitude. And by comparing paleomagnetic data from rocks of different ages, they can track the movement of continents and tectonic plates back through hundreds of millions, even billions, of years. The Archean cratons have been in many places. Rocks that now sit in South Africa were once near the equator. Rocks now in Canada have drifted from the southern hemisphere. The continents have waltzed across the face of the Earth, guided by the mantle currents below, and the record of their journey is written in the magnetic minerals of the ancient rocks they carried with them. The Earth moves. She has always moved. And the rock remembers where she has been. So when we tell you about the Archean, about the dark oceans, the microbial mats, the comatite eruptions, the first rains, we are not inventing. We are not speculating beyond what the evidence allows. We are reading a record. An incomplete record. Certainly much has been lost, subducted back into the mantle, worn away by erosion, overwritten by younger geology. The Archean, being the oldest, is also the most eroded, the most transformed, the hardest to read. But what remains is real. It is there, in the rock. In the zircon crystals of the Jack Hills and the pillow lavas of the Pilbara and the banded iron formations of the Karpval Craton and the ancient gneisses of the Canadian Shield. The evidence is there, patient and precise, waiting for the right questions. The Earth has been telling her story all along. We are just beginning to learn how to listen. As you rest, as the thoughts of the day become softer, less insistent, consider that the ground beneath you is a document. Every layer of rock below the soil holds some record of the time in which it formed. The story goes down and down, getting older as it goes, until at some great depth the rock is Archean, older than anything living, older than the first cell, older than the first rain. You are lying on top of a library. The oldest library there is. And tonight, just a little of it has been read to you. Sleep well. There is a particular feeling that comes from standing on high ground. From a hilltop, from a cliff edge, from the summit of a mountain, that feeling of extent. Of the world spreading out below and around you, of distance made visible, of the curve of the horizon reminding you, quietly, that the world is large and you are small, and both of these things are fine. In the early Archean, there was no high ground. There were no hills. No cliffs. No mountains worthy of the name. The ocean was vast, warm, global, and from it, here and there, the dark heads of volcanic islands broke the surface, steaming and smoking, battered by waves and storms, geologically young and geologically temporary. Not places you could stand for long, even if standing had yet been invented. But slowly, with the patience that is the defining quality of this entire story, things were changing. The first continents were being born. We touched on the mechanics of this in the second segment. The TTG rocks, tonalite, transurmite, granodiorite, rising from partially melted oceanic crust, lighter than what they came from, accumulating at the surface in growing masses of buoyant pale rock. The cratons forming, thickening, developing the deep keels of cold, dense lithosphere that would eventually stabilize them against the convective churning below. But mechanics, described in isolation, can make a process sound cleaner and more orderly than it was. The reality of Archean continent formation was messier, more violent, more contingent than any simple model suggests. It was not a single process but many operating simultaneously, interacting, sometimes reinforcing and sometimes counteracting one another. Let us try to see it whole. The Archean Ocean is not still. It has currents driven by the heat of the volcanic ridges below, by the temperature difference between the equatorial and polar regions, by the rotation of the Earth. The tides are dramatic, far more dramatic than today, because the Moon is younger and closer, not dramatically closer, perhaps a few tens of thousands of kilometers nearer than its current distance of 380,000 kilometers, but close enough that the tidal forces are noticeably stronger. The Archean Ocean heaves and surges in tidal rhythms that are slightly faster, slightly more forceful than anything the modern Earth experiences. Against this moving, tidal, storm-lashed ocean, the first small cratons sit like stepping stones. They are scattered. They have no particular organization. They are simply wherever the geology happened to produce buoyant crust, wherever a subduction zone was active, wherever a mantle plume punched up from below and produced a large outpouring of rock that was later reworked into TTG material. Each craton is its own small world, surrounded by ocean, unconnected to the others. But they are drifting. The mantle convection that drives the plates does not respect the boundaries of the small early cratons. They are carried by the flow slowly, over millions of years, nudged this way and then that, following the patterns of a convective system that is gradually evolving as the mantle cools. And sometimes, not always, but sometimes two cratons drift toward each other. When they meet, they do not simply stop. They cannot sink, they are too buoyant for that. Instead they collide, and the collision produces exactly what you might expect from two pieces of rigid, ancient rock running into each other at the speed at which continents move: compression. Buckling. The rock between them crumpling and folding and, in places, being thrust upward. The first mountains. Not the soaring, snow-capped ranges of later eons that require a scale of continental collision that the small Archean cratons could not yet produce. But genuine elevated terrain. Real topographic relief. High ground, for the first time, above the level of the sea. And with high ground comes something new: erosion. Rain falls on high ground and runs downhill. As it runs, it carries with it fragments of the rock it passes over: sand grains, clay particles, dissolved minerals. This material is transported to the sea, where it settles as sediment, accumulating in layers on the shallow seafloor around the margins of the growing cratons. These sediments become sedimentary rock sandstones, shales, conglomerates, and they are archives of a different kind from the igneous rocks we have been discussing. Where igneous rocks record the conditions of their crystallization from magma, sedimentary rocks record the environment of their deposition. The size of the grains tells you the energy of the water that deposited them. The composition tells you what rock was being eroded upstream. The presence of certain minerals including, vitally, pyrite and uraninite, which are unstable in the presence of oxygen, tells you something about the atmosphere under which the erosion occurred. In the Archean sedimentary record, those oxygen-sensitive minerals are found intact. Rounded by water transport, clearly carried by ancient rivers, deposited in ancient deltas and undissolved. Still there. Which tells us something important: the atmosphere through which those rivers flowed had no free oxygen to speak of. The air was reducing, not oxidizing. The cyanobacteria were photosynthesizing, yes, but the oxygen they produced was still being consumed by the iron in the ocean before it could accumulate in the air. The sediments are reading the atmosphere. And the atmosphere, in the Archean, is still anaerobic. The collision and assembly of cratons is a process that geologists call terrain accretion, the welding together of distinct geological fragments into larger composite blocks. It is happening throughout the Archean, and it accelerates through the middle and late parts of the Eon as the number and size of stable crustal fragments increases. One of the best studied examples is the assembly of what would eventually become the core of the North American continent. The Superior Province, a vast expanse of Archean rock stretching from Ontario and Quebec westward through Manitoba, the largest exposure of Archean crust on Earth, was assembled from multiple distinct terrains over a period stretching from about 3 billion to 2.7 billion years ago. Each terrain had its own geological history, its own age, its own rock types. The suture zones between them, the scars of ancient collisions, are still visible in the rock record, marked by distinctive mineral assemblages and structural fabrics that speak of compression and heat and the grinding of ancient crust against ancient crust. The Superior Province is, in a sense, a jigsaw puzzle assembled from pieces that were scattered across an ancient ocean. It took 300 million years to put together. And it has been sitting there, essentially unchanged, for 2.7 billion years since. The Karpval Craton of southern Africa is another of the world's great Archean survivors. It underlies much of present-day South Africa, Zimbabwe, and Botswana, and it contains some of the best-preserved Archean sedimentary sequences on Earth. The Witwatersrand Basin, famous not only for its geology but for the extraordinary gold deposits laid down in ancient river systems 3 billion years ago. The gold of the Witwatersrand is Archean gold eroded from ancient mountains, transported by ancient rivers, concentrated in ancient deltas, and preserved through everything since. When a miner descends into a South African gold mine, they are descending into the Archean. They are working in rock laid down 3 billion years ago, in rivers that flowed across a continent that no longer exists in that form, under a sky that had no oxygen. The gold they extract has been sitting there, in the dark, longer than complex animal life has existed anywhere on Earth. As the Archean progresses, the scattered cratons begin to coalesce into something larger. Not yet the familiar continents of today, those are still billions of years away, their shapes determined by tectonic events that have not yet happened. But something like protocontinents, larger, more stable landmasses, rising more consistently above the ocean surface, developing the thick, deep roots of the lithosphere that will make them almost indestructible. With more land above sea level, the world begins to change in subtle but important ways. The weathering of continental rock, the chemical breakdown of silicate minerals by rainwater and carbon dioxide begins to consume CO from the atmosphere in earnest. This process, the silicate weathering feedback, is one of the Earth's most important long-term regulators of climate. When the planet warms, weathering accelerates, consuming more CO, reducing the greenhouse effect and cooling the planet back down. When it cools, weathering slows, CO accumulates, and the greenhouse warms it back up. It is a thermostat, built from rock and rain and time. And it has been operating, with occasional dramatic failures, for as long as continents have been above sea level. The Earth, even now, is beginning to regulate herself. Stand, for a moment, on one of those early Archean protocontinents. 3 billion years ago, perhaps late in the Archean, when the landmasses are larger and more stable than they were in the beginning, but still quite different from anything we would recognize. The rock underfoot is pale gray and white and pinkish, the coarse-grained TTG material that built the continental cores. It is bare. There is no soil, not in any sense we would recognize, no organic matter, no root systems, no earthworms turning the mineral particles into the rich, dark loam of a living landscape. There is only rock, and the thin chemical alteration of its upper surface by rainwater, and the dust. The sky is still hazy, still lacking oxygen in any significant concentration. But something has changed in it or is beginning to change. The methane that dominated the early Archean atmosphere is slowly being processed, slowly being replaced, as the cyanobacteria continue their patient work. The haze is thinning, marginally, over millions of years. It is still not a sky you could breathe. But it is, very slightly, beginning to move toward one. The wind blows across the bare rock. There is nothing to slow it, nothing to break it, no trees, no grass, no scrub. The landscape is purely geological. Just rock, and rain when it comes, and the wind, and somewhere at the horizon the gleam of the ocean. But the ocean is closer than it used to be. The land is higher. The continents are growing. Something is being built here. Something large and lasting and consequential. Not quickly, nothing in this story happens quickly. But with a certainty that, in retrospect, feels almost like purpose. The Earth is assembling the stage on which everything else will eventually play out. There is an old idea, not a scientific one, but an intuitive one, the kind that lives in the body rather than the mind, that the ground beneath us is permanent, stable, fixed. That the mountains were always there, that the continents have always had their present shapes, that the world we know has always been more or less the world that was. We know now that this is not true. We know that the ground has moved, is moving, will move again. That the continents are in transit, have always been in transit, drifting on the slow currents of the mantle beneath them. That the mountains rise and are worn down, and the oceans open and close, and nothing about the surface of the Earth is fixed on any timescale longer than a geological moment. And yet, the oldest rock, the Archean cratons, the ancient hearts of the continents, has endured. For billion years of everything the Earth could throw at it, and it is still there. Still at the surface. Still solid underfoot, in those remote northern places where the younger rock has been stripped away and the ancient grey-pink gneiss emerges into the light. Some things do last. Not because they are unchanging, the cratons have been deformed and intruded and metamorphosed many times over. But because they are resilient. Because what they are made of, and how they are rooted, makes them capable of absorbing punishment and persisting. The oldest ground persists. There is something in that thought worth carrying into sleep. Let your body be heavy now. Let the weight of it settle, like sediment settling on an ancient seafloor, slowly, completely, finding its level. Let the day's motion stop. You are resting on ground that is very, very old. And it will hold you. It always has. Water is the strangest substance on Earth. Not the rarest. Not the most chemically reactive. Not the heaviest or the lightest or the most energetic. But the strangest, the most quietly extraordinary, because of what it does. Because of how it behaves. Because of the particular combination of properties it possesses that makes it, uniquely, the medium in which life as we know it becomes possible. Water is a universal solvent, not literally universal, but more capable of dissolving other substances than almost any other liquid. It dissolves salts, minerals, gases, and organic compounds. It carries things in solution. It brings them into contact with each other. It is the medium of chemistry, the context in which reactions happen, the stage on which the molecular drama of life plays out. Water is also anomalously heat-stable. It absorbs enormous amounts of heat before its temperature rises, and releases that heat slowly. This makes it a buffer, a moderator, a substance that resists extremes, that keeps the temperature of whatever contains it from swinging too wildly in either direction. And water is less dense as a solid than as a liquid, which is why ice floats. This seems like a trivial detail until you consider the alternative. If ice sank, the oceans would freeze from the bottom up, and once frozen, they would be almost impossible to melt again. The fact that ice floats means that even in the coldest conditions, the ocean surface may freeze but the water below remains liquid. Life can persist beneath the ice. Chemistry can continue. These are not accidents. They are consequences of the molecular structure of water, 2 hydrogen atoms and 1 oxygen, bound at a specific angle, creating a molecule that is slightly polar, slightly attracted to itself, forming the hydrogen bonds that give water its peculiar and life-enabling properties. The Archean Ocean is made of this strange and wonderful substance. And it is doing remarkable things. The chemistry of the Archean Ocean is unlike the chemistry of any ocean that has existed since. The most striking difference is the iron. In the modern ocean, dissolved iron is vanishingly scarce, a limiting nutrient for marine life, present in concentration so low that adding iron to patches of the modern ocean causes explosive blooms of phytoplankton, as the organisms rush to take advantage of a suddenly available resource. The modern ocean is iron poor because oxygen is iron poor's cause. Iron reacts with oxygen, precipitates as iron oxide, and sinks. In an oxygenated ocean, iron cannot stay dissolved for long. But the Archean Ocean has no oxygen. And so the iron stays dissolved. In enormous quantities, concentrations perhaps 1,000 times higher than today. The Archean Ocean is, effectively, a dilute solution of iron. And iron is not merely a curiosity, it is a catalyst. A facilitator of chemical reactions. A key component of many of the most fundamental molecular machines of life. The iron-rich Archean Ocean is, in this sense, a naturally buffered chemical laboratory. The raw materials for the machinery of life are present everywhere, in solution, available to whatever chemistry can make use of them. The ocean is also rich in silica, dissolved silicon dioxide, leached from the volcanic rock by the circulating seawater. In the modern ocean, silica is rapidly consumed by organisms, diatoms, radiolarians, sponges that build their shells from it. But in the Archean, before those silica-hungry organisms evolved, silica accumulated freely in the water. The ocean is supersaturated with it. It precipitates spontaneously in some places, forming the chert deposits that will eventually preserve some of the oldest microfossils we know. And the ocean is warm. Much warmer than today. The average temperature of the Archean deep ocean may have been somewhere between 50 and 80 degrees Celsius, temperatures that would feel, to a modern human swimmer, not like an ocean at all but like a very hot bath. The surface waters in the tropics may have been warmer still. This warmth matters for chemistry. Chemical reactions, broadly speaking, happen faster at higher temperatures. The warm Archean Ocean is a faster ocean. In a chemical sense, reactions that would take millennia in cold water happen in centuries, or decades, or years. The pace of molecular change is elevated. Chemistry is urgent, productive, energetic. Into this warm, iron-rich, silica-saturated, chemically energetic ocean life has arrived. And life, once it arrives in an environment, does not merely inhabit it. It begins immediately, inevitably, to change it. The earliest organisms were taking in molecules from the ocean around them and releasing others. They were processing iron, sulfur, carbon, nitrogen, cycling these elements through their chemistry and returning them, transformed, to the water. They were, in the most fundamental sense, doing geochemistry, adding their metabolic activity to the already complex chemical processes of the ocean, making the whole system more intricate, more interconnected, more dynamic. This is the beginning of what we now call biogeochemical cycling, the movement of elements through living organisms as part of their larger cycling through the Earth system. The carbon cycle, the nitrogen cycle, the sulfur cycle, the phosphorus cycle. All of them have biological components, parts of the cycle that pass through living things, and all of those biological components were being established, in their most primitive forms, in the Archean Ocean. Life did not arrive in the ocean and leave it unchanged. From the very beginning, life and ocean were in conversation, each shaping the other, each responding to the changes the other made. The nitrogen cycle deserves particular attention here, because nitrogen is something that life cannot do without, and the form in which nitrogen exists in the environment determines, to a large degree, how much life can exist at all. The Archean atmosphere is rich in nitrogen. It is, in fact, the dominant gas, just as it is today. But atmospheric nitrogen N, two nitrogen atoms bonded together, is almost completely inert. It will not react. It cannot be used directly by most organisms. It needs to be fixed, broken apart and combined with hydrogen to form ammonia, or combined with oxygen to form nitrates before it becomes biologically useful. In the modern world, nitrogen fixation is performed primarily by bacteria, a relatively small group of microorganisms that carry a remarkable enzyme called nitrogenase, which can do what almost no other chemistry can: break the extraordinarily strong triple bond of the N molecule at ambient temperature and pressure. In the Archean, nitrogen fixation is beginning to evolve. The earliest nitrogen-fixing organisms are emerging, developing the metabolic toolkit that allows them to tap the vast reservoir of atmospheric nitrogen and make it available to the rest of life. This is a profound expansion of life's resource base. Instead of depending entirely on whatever fixed nitrogen is present in the environment, life gains the ability to manufacture its own. Another lock picked. Another door opened. The phosphorus story is quieter but no less important. Phosphorus is the backbone of the energy currency of life. ATP adenosine triphosphate, the molecule that powers almost every biological process, is, at its heart, a phosphorus compound. The double helix of DNA, the hereditary molecule that encodes the instructions for building every living thing, is linked together by a phosphate backbone. Every cell membrane contains phospholipids. Phosphorus is everywhere in the machinery of life, essential and irreplaceable. And phosphorus, unlike nitrogen, cannot be fixed from the atmosphere. It comes entirely from the rock dissolved from minerals by the weathering of the continents and carried to the ocean by rivers. In the modern ocean, phosphorus is often the limiting nutrient, the resource whose scarcity most constrains how much life can exist. Add phosphorus to the modern ocean, and life blooms. In the Archean, the situation is complex. The warm, volcanic ocean is in some places richer in phosphorus than today's ocean. There is more volcanic and hydrothermal activity releasing it from the rock, and less biology consuming it before it reaches the open water. But in other places and times, the chemistry of the iron-rich ocean may have caused phosphorus to bind to the iron particles and sink out of the water, removing it from the biological realm. The availability of phosphorus in the Archean Ocean varies in space and time, and those variations shape where life is most abundant, most active, most diverse. Life clusters where the chemistry is richest. It always has. Sulfur is the third great element of Archean life. In an ocean without oxygen, sulfur exists in a reduced form as hydrogen sulfide and dissolved sulfide compounds, the same sulfurous chemistry that we associate today with volcanic vents and rotten eggs. And for many of the earliest organisms, sulfur is food. They are sulfur reducers or sulfur oxidizers, running their metabolisms on the chemical energy available from sulfur chemistry, producing or consuming hydrogen sulfide as they go. The evidence of this ancient sulfur metabolism is preserved in the rock record in the isotope ratios of sulfur atoms in ancient sediments, which carry the signature of biological processing just as carbon isotopes carry the signature of photosynthesis. The sulfur isotopes in Archean rocks tell a detailed story of which organisms were present, in which environments, and how active their sulfur cycling was. What they tell us is that the Archean Ocean was alive with sulfur chemistry. That organisms were working this cycle, in the deep sea and in the shallow margins, processing sulfur compounds and leaving their isotopic fingerprints in the sediments that accumulated below them. The ocean was not a backdrop for life. It was a participant. It and life were running the chemistry of the world together, each dependent on the other, each changed by the other, in a partnership that has continued, in various forms, to this day. There is something deeply moving about the biogeochemical cycles, about the idea that the elements of which we are made have been cycling through the Earth system for billions of years. The carbon in you has been in the atmosphere, in the ocean, in the bodies of organisms, in rock, and back again, many thousands of times. The nitrogen in your DNA has passed through the metabolism of countless organisms before it reached you. The phosphorus in your bones was once dissolved in an Archean sea. You are not a collection of atoms that belongs to you. You are a temporary arrangement, a particularly interesting and self-aware arrangement of atoms that have been in constant circulation since before the Earth was cool. They will be in circulation long after you. They will pass through other organisms, other rocks, other oceans, for billions of years to come. The atoms are on loan. The arrangement is what is yours. The Archean Ocean understood this, in its way. It was already cycling, moving carbon and nitrogen and sulfur and phosphorus and iron through an elaborate network of geological and biological processes. It was already, in its ancient and unconscious way, doing the work that keeps the chemistry of a living planet in balance. It was learning how to be a living world. And the organisms in it were learning along with it, evolving new metabolisms, new ways of capturing energy, new chemical tricks that expanded what was possible. Each new capability built on the last. Each new metabolic pathway opened new resources, new environments, new possibilities for the life that would follow. The Archean Ocean is not a simple place. It is a laboratory of staggering complexity, running thousands of simultaneous experiments, most of which will fail, some of which will succeed, and a very few of which will change everything. The ocean tonight, the real ocean, somewhere beyond your walls and your window, whatever distance away it may be, is running the same cycles. More complex now, more biological, more oxidized. But the same cycles, in their essence. Carbon moving through algae and bacteria and fish and sediment. Nitrogen fixed and released and fixed again. Iron cycling through the water column, carried up by upwelling, sinking down with the bodies of organisms that took it in. The chemistry of the modern ocean was written in the Archean. The cycles were established then, primitive, simple, but present. And every modification, every elaboration, every new organism and new metabolic trick added since has been built on that ancient foundation. The ocean remembers the Archean. It is still, in many ways, running on Archean chemistry. Breathe in. The oxygen in that breath was produced by organisms doing what the cyanobacteria learned to do in the Archean Ocean. The carbon dioxide you breathe out will enter the atmosphere and eventually, over geological time, cycle back through rock and ocean and organism, just as it has always done. You are part of the cycle. You always have been. Rest now, inside that. The chemistry will continue while you sleep. It always does. Every long story has its moments of crisis. Not because a crisis is inevitable, exactly, but because the conditions that make a story rich and complex are the same conditions that make it unstable. A world full of competing forces, of chemical gradients and heat flows and the slow accumulation of consequences. Such a world does not move smoothly from one state to the next. It lurches. It oscillates. It finds a kind of rough equilibrium, and then something shifts, and the equilibrium is broken, and a new one must be found. The Archean is no exception. Beneath the slow and patient rhythms of mantle convection and continental growth and the quiet metabolizing of microbial mats, beneath all of that, the Earth is a system under stress. Running hot. Managing competing demands. Walking, as we noted before, a knife's edge between freezing and boiling. And sometimes she comes close to the edge. Let us begin with cold. The paradox of the Archean climate begins with the sun. The Sun, as it exists today, is a middle-aged star approximately 4.5 billion years into its expected 10 billion-year life. In the middle of that life, a star is at its most stable, its luminosity changing only slowly over millions of years. But in its youth, a star runs cooler. The young Sun, when the Archean began, was perhaps 70 to 75% as luminous as it is today. It put out significantly less heat and light. This creates a puzzle that geologists call the faint young sun paradox. Simple calculations suggest that with a sun 25 to 30% dimmer than today, and an atmosphere similar to the modern one, the Earth's surface should have been frozen solid throughout most of the Archean. The ocean should have been ice. The temperature should have been far below the freezing point of water. And yet the geological record tells us clearly, unambiguously, that the Archean Earth had liquid oceans, had warm surface temperatures, had, in places, conditions that seem almost tropical. The paradox is real, and it has occupied geologists and climatologists for decades. The most widely accepted resolution is the greenhouse. The Archean atmosphere was far richer than today in greenhouse gases. Carbon dioxide, certainly, outgassed from the abundant volcanism of the young Earth. But also methane, produced by the methane-generating microorganisms, the methanogens that were among the earliest and most successful life forms in the Archean Ocean. Methane is a potent greenhouse gas, 25 times more effective at trapping heat than coal over a century timescale. The combination of more coal, more methane, a thick and heat-retaining atmospheric blanket compensated for the dimmer sun. The greenhouse effect, which in the modern world is a cause for concern, was in the Archean the very thing that kept the oceans liquid and life possible. The Earth was keeping herself warm, with the help of her own atmosphere and the microbes breathing into it. But the balance was not always maintained. There are hints in the geological record contested, debated, but persistent that the Archean saw episodes of significant glaciation. Not the full planetary freeze of later eons, perhaps, but periods of cooling significant enough to leave glacial deposits, diamictites, in the rock record. These are chaotic, unsorted mixtures of boulders and fine sediment, the signature of glacial activity, of ice sheets grinding rock and depositing it without the sorting that running water would impose. The mechanisms that might drive such cooling are several. A reduction in volcanic activity and therefore in co-outgassing could tip the balance toward cold if it persisted long enough. A change in the methane budget, perhaps driven by a shift in the microbial community, could remove a significant source of greenhouse warming. Or simply the natural variability of a system running on as many interacting feedbacks as the early Earth, a system capable of amplifying small perturbations into large swings. Each time the Earth cooled significantly, the silicate weathering thermostat would eventually intervene. As temperature dropped, weathering slowed, and began to accumulate again unweathered, exhaled by volcanoes into an atmosphere that was consuming less of it. Slowly, the greenhouse would rebuild. Slowly, the temperature would recover. The Earth pulled herself back from the cold. Every time. At least, every time in the Archean. There would come a later time hundreds of millions of years into the future when the thermostat would fail more dramatically. When the ice would spread all the way to the equator. That story belongs to another episode. For now, in the Archean, the recoveries are successful, and the liquid ocean persists. Now the heat. If cold is one extreme, the other is the episodic, catastrophic violence of large igneous province eruptions, events in which the mantle delivers, in a relatively short geological time, vast quantities of lava to the surface. Not from a single volcano but from an entire region of the crust, cracked open by a rising mantle plume, flooding with basalt over timescales of tens of thousands to hundreds of thousands of years. In the modern geological record, the consequences of large igneous province eruptions are dramatic and well documented. The Deccan Traps of India, erupting around 66 million years ago, contributed alongside the Chicxulub asteroid impact to the end Cretaceous mass extinction. The Siberian Traps, erupting 252 million years ago, drove the most severe mass extinction in Earth's history, killing perhaps 96% of marine species. In the Archean, such events were more frequent. The hotter mantle produced plumes more readily. The thinner crust was more easily breached. Large igneous province eruptions may have punctuated the Archean at intervals, each one injecting enormous quantities of CO and sulfur dioxide into the atmosphere, each one potentially causing both short-term cooling from the sulfur aerosols, which reflect sunlight, and longer-term warming from the CO. The short-term cooling could be severe. A sufficiently large eruption fills the stratosphere with sulfur dioxide, which converts to sulfate aerosols, which reflect incoming sunlight and drop global temperatures dramatically within months. Volcanic winter is the same mechanism by which large asteroid impacts cause cooling, but driven by volcanic chemistry rather than impact ejecta. In the Archean, where life is entirely microbial, entirely aquatic, these volcanic winters are not the civilization-ending catastrophes they would be for a world with complex ecosystems. But they are disruptions. They stress the microbial communities. They change the chemistry of the ocean. They eliminate some lineages, open niches for others, drive the evolution of new tolerances and new capabilities. Catastrophe, in this story, is also a kind of engine. The asteroid bombardment, too, continues into the Archean, though at a declining rate as the solar system gradually clears the debris of its formation. In the very early Archean, the impacts are still frequent enough to be geologically significant. Large impacts superheat the ocean surface, potentially boiling away the upper layers of the sea, sterilizing the shallow environments where some of the earliest life may be clustering. They deliver energy to the deep ocean floor, creating hydrothermal activity, disrupting and perhaps also seeding new environments for microbial colonization. There is evidence in the Archean rock record of spheral layers, thin layers of tiny glass beads, created when an asteroid impacts vaporize rock that then recondenses as it falls back through the atmosphere. These layers are found in the ancient sediments of South Africa and Australia, and they record impacts of extraordinary scale events that would, by modern standards, be civilization-ending catastrophes, but in the context of the Archean are simply part of the background noise of a young solar system still in the process of tidying itself up. The largest of these Archean impacts may have had oceanic consequences that persisted for thousands of years, tsunamis that reshaped coastlines, chemical changes to the ocean from the injected material, disruptions to the microbial ecosystems of the shallow seas. And yet life persisted. Through every impact, every volcanic winter, every glacial episode. The microbial communities, distributed through the ocean and into the rock, were resilient in a way that more complex life rarely is. Some populations would be destroyed. Others would survive in refugia deep in the ocean, in hydrothermal vents, in the rock itself, and from those refugia, they would recolonize the disturbed environments when conditions improved. Life, once established, has proven extraordinarily difficult to erase. There is a concept in ecology called resilience, the ability of a system to absorb disturbance and return to something like its previous state. And the Archean Earth, despite everything, is a resilient system. The same feedbacks that regulate its climate, the silicate weathering thermostat, the biological carbon pump, the ocean's capacity to absorb heat also buffer it against the extremes of volcanic winters and asteroid impacts and glacial episodes. Not perfectly. Not without cost. The disruptions leave their mark in the rock record, in the evolutionary history of the microbial lineages that survived each crisis, in the chemistry of the oceans that was reset by each major event. The Archean is not a smooth story of steady progress. It is a story of forward motion interrupted by setback, of equilibrium broken and rebuilt, of a system learning, through repeated crisis, how to be more robust. She is not delicate, the early Earth. She is tough, in the way that only very old things are tough, not because she has avoided damage, but because she has absorbed it, again and again, and persisted. One more extreme deserves mention, the rotation. We have touched on this before, the early Earth spinning faster, the days shorter than today. In the Archean, a day may be as short as 12 hours, possibly less in the very earliest period. The Earth is gradually slowing, braked by the tidal friction of the Moon's gravitational pull on the oceans, transferring the Earth's rotational energy to the Moon's orbit, pushing the moon slowly outward and lengthening the day by roughly 2 milliseconds per century, a rate so slow as to be imperceptible on a human timescale, but significant over billions of years. The consequence of faster rotation is a different climate. Faster spin means stronger Coriolis force is the deflection of moving air and water by the rotation of the Earth, which means different patterns of atmospheric and oceanic circulation. The Archean climate is not just warmer and more volcanic than today's. It is structured differently. The wind patterns, the ocean currents, the distribution of heat around the planet are all shaped by a planet spinning noticeably faster than the one we live on. Every detail is different. And every detail matters. The pace softens here. We are coming toward the close. The Archean is a world of extremes. Of heat and occasional cold. Of violent volcanic episodes and the slow, patient chemistry of microbial life working in between. Of asteroid impacts and their eventual fading. Of a sun gradually brightening, a moon gradually retreating, a day gradually lengthening. Of a climate walking its knife's edge and, so far, not falling. It is not a comfortable world, by any human measure. But comfort is not what the Archean is about. The Archean is about establishment. About laying down the foundations of the crust, of the ocean chemistry, of the biological lineages that everything else will be built upon. And foundations, by their nature, must be strong. Must be tested. Must survive the stresses that are brought to bear on them before the building above can be trusted. The Archean is the testing of the foundations. And they hold. Think of the things that have held in your own life. The things that have been tested, pressured, stressed and have not broken. The relationships, the values, the habits of mind that have survived difficulty and emerged, if anything, more solid for having been through it. Resilience is not the absence of challenge. It is what is left after the challenge has passed. The Earth knows this. She has always known it. She has been tested since before the first morning, and she is still here. And so, tonight, are you? Let the extremes of the day dissolve. Let whatever has pressed on you release. You have held. You are holding still. Rest in that. Evolution does not hurry. This is perhaps the hardest thing about it to hold in the mind, harder even than the timescales, harder than the chemistry, harder than the sheer improbability of any of it. Evolution does not have a destination. It does not know where it is going. It does not try. It simply runs a process, not a plan, sifting through variation, discarding what fails, keeping what works, accumulating the kept things over generations beyond counting. It is not fast. It is not directed. And it is over sufficient time capable of producing results of staggering complexity and beauty from the simplest of beginnings. In the Archean Ocean, with 1.5 billion years available to it, it has plenty of time to work. The mechanism of evolution is simple to state and endlessly rich in its consequences. Organisms reproduce. In reproduction, errors occur, mutations, tiny changes in the genetic sequence, introduced by the imperfect copying of DNA or RNA, or by the chemical damage of radiation or reactive molecules. Most mutations are harmful or neutral. A very few are beneficial. They make an organism slightly better at surviving or reproducing in its particular environment. Those beneficial mutations are preserved. The organisms that carry them leave more offspring. The offspring carry the mutation. Over generations, over thousands and millions of years, the beneficial mutations spread through the population. The population changes. It adapts to its environment. And when the environment changes, as it does, constantly, in the Archean the population must adapt again, or dwindle, or find a refuge where the old way of doing things still works. This is natural selection. And in the Archean Ocean, it is running continuously, in every environment, in every population of organisms, across the full span of 1.5 billion years. The diversity that results is, even in this early and entirely microbial world, remarkable. The earliest life, as we discussed, was most likely a community of chemolithotrophic organisms feeding on chemical energy from the geological environment. But very quickly, in geological terms, this simple beginning branches. Different lineages find different energy sources. Different metabolisms evolve. Different chemical environments are colonized. By the Middle Archean 3 billion years ago, the ocean already contained a remarkable variety of microbial life. There are the methanogens, producing methane as a metabolic byproduct, thriving in the anaerobic depths of the ocean and sediment. There are the sulfur reducers, running their energy on the reduction of sulfate to sulfide. There are the iron reducers, using dissolved iron as an electron acceptor in their metabolism, processing the vast iron reserves of the Archean Sea. And there are the photosynthesizers, first the anoxygenic kind, using hydrogen sulfide as their electron donor, and then, in an evolutionary step of world-altering consequence, the cyanobacteria with their water-splitting, oxygen-producing machinery. Each of these metabolic strategies is a different way of extracting energy from the Archean environment. Each one is a solution to the fundamental problem of life: how to maintain organization and function in a universe that is constantly pushing toward disorder. The genetic machinery underlying all of this diversity is itself a subject of profound scientific fascination. All life on Earth shares the same basic genetic code. The same 20 amino acids, specified by the same triplet codons in the same DNA language, translated by the same basic ribosomal machinery. This universality is one of the most powerful lines of evidence that all life on Earth is descended from a single common ancestor, a population of organisms that lived, most likely, in the Archean Ocean, and from which every subsequent lineage has descended without a break. This ancestor, referred to in the scientific literature as Luca, the last universal common ancestor, was not the first life. It was the survivor. The lineage that, at some point in the early Archean, outcompeted or simply outlasted all the other early experiments in self-replication and left descendants that filled the world. Luca was almost certainly a prokaryote lacking a nucleus, lacking complex internal structures. But it already possessed the core genetic and metabolic machinery that all subsequent life would inherit: ribosomes for making proteins, a genetic code for encoding them, cell membranes for maintaining the chemical distinction between inside and outside. It had, in essence, solved the fundamental problems of being alive, and its solutions were good enough that they have been conserved, in their essentials, for 4 billion years. We do not know exactly what Luca looked like. We cannot isolate it, observe it, culture it. But we can infer its properties from the features shared by all living things, the common ground that every lineage has inherited from that founding population. And what those inferences suggest is a thermophile, a heat lover, thriving at high temperatures, metabolically adapted to the warm, chemically rich environment of a hydrothermal system. Life's deepest roots reach down into hot rock and hot water. From Luca, the tree of life begins to branch. The first great division, the deepest split in the history of life, is between the bacteria and the archaea. These are the two primary domains of prokaryotic life, and they diverged, the molecular evidence suggests, very early in the Archean, perhaps as far back as 3.8 billion years ago, perhaps earlier. The bacteria and archaea look superficially similar, both small, both single-celled, both lacking a nucleus. But at the molecular level they are profoundly different. Their cell membranes are constructed from different types of lipids, not just different molecules, but molecules built on a fundamentally different chemical framework, as though two architects received the same brief and produced buildings with entirely different structural systems. Their ribosomes, while similar in function, differ enough in their molecular details that antibiotics which target bacterial ribosomes do not affect archaeal ones, a difference with real consequences for medicine, billions of years after the split. The archaea, despite their name, are not the most ancient of the two domains. The split between bacteria and archaea does not tell us which came first, merely that they diverged, early and decisively, from their common ancestor. What it does tell us is that by the Middle Archean, the tree of life already had deep roots and was branching vigorously. The archaea have proven to be extraordinary organisms, found in the most extreme environments on Earth, the extremophiles. Thermophiles in hot springs. Halophiles in salt lakes are so concentrated that the water is dense enough to float in. Acidophils in volcanic pools where the pH approaches zero. Methanogens in the airless depths of swamps and the intestinal tracts of animals. Psychrophiles in Antarctic ice. Their tolerance of extremes is not a coincidence. The early Earth was an extreme environment by any modern measure: hot, acidic, anaerobic, chemically challenging in ways the modern Earth rarely achieves outside of very specialized locations. The organisms that thrived in that world were the ones equipped for extremity. And the archaea, in their various lineages, have retained and elaborated those ancestral adaptations across 4 billion years of evolution. When we want to understand what early life was like, we look at archaea. They are, in a sense, living windows into the deep past, not unchanged, never unchanged, but retaining in their biology echoes of a much older world. The Archean Ocean, over its 1.5 billion-year span, sees the evolution of almost every fundamental metabolic strategy that life will ever use. Fermentation, the extraction of energy from organic molecules without oxygen, is ancient, present in both bacteria and archaea, almost certainly one of the earliest metabolic strategies. Methanogenesis, the production of methane by combining hydrogen and carbon dioxide, is also ancient, the domain of the archaea, and as we have noted, enormously consequential for the greenhouse warming of the early Earth. Sulfate reduction, iron reduction, nitrogen fixation, all of these evolve in the Archean, expanding life's resource base, connecting it more deeply into the geochemical cycles of the planet. And then photosynthesis. The evolution of anoxygenic photosynthesis, the capture of sunlight using hydrogen sulfide rather than water, releasing sulfur rather than oxygen, is an early Archean event, likely predating 3.5 billion years ago. It is a profound expansion of life's energy budget, allowing organisms to tap the essentially unlimited energy of sunlight rather than depending on the locally available chemical energy of the geological environment. Oxygenic photosynthesis, the water-splitting, oxygen-releasing version perfected by the cyanobacteria, evolves later, and its timing is debated. Some researchers place it as early as 3 billion years ago. Others argue it emerged closer to 2.7 billion years ago. Geological evidence, the appearance of banded iron formations, the isotopic signatures in ancient rocks suggests that by 2.7 billion years ago, oxygenic photosynthesis was well established and spreading. Either way, in the context of the Archean, it is a late development. Life spent perhaps 1 billion years developing and refining anoxygenic photosynthesis before the cyanobacteria arrived with their more powerful, more consequential version. Evolution is not hasty. There is one more development worth dwelling on, one that does not quite happen in the Archean but whose seeds are perhaps planted there. The evolution of the eukaryotic cell. All the life we have discussed so far is prokaryotic, simple, nucleated, small. The eukaryotic cell, the kind that makes up every cell in your body, and the cells of every plant, every fungus, every animal on Earth, is a different thing entirely. It has a nucleus enclosed in its own membrane. It has complex internal structures, the mitochondria that generate energy, the chloroplasts in plant cells that perform photosynthesis, the elaborate scaffolding of the cytoskeleton that gives the cell its shape and allows it to move. The eukaryotic cell almost certainly arose from a merger of an event called endosymbiosis, in which one prokaryotic cell engulfed another and, instead of digesting it, incorporated it as a permanent internal partner. The mitochondrion was once a free-living bacterium. It was taken up by an archaeal host cell, and instead of being destroyed, it survived, retained its own DNA, and over time became inseparable from the cell that contained it. The merger gave the host cell access to the bacterium's metabolic capabilities, and gave the bacterium a protected internal environment. Two organisms became one. This event, which the fossil and molecular evidence places at approximately 2 billion years ago, just at the boundary of the Archean and the Proterozoic, does not happen in our story tonight. But the conditions for it are being laid down throughout the Archean. The bacterial lineage that will eventually become the mitochondrion is evolving in the Archean Ocean. The archaeal lineage that will eventually become the host cell is evolving there too. They are passing each other in the dark water of the ancient sea, billions of years before they will combine into something that will eventually become capable of building every complex organism on Earth. Including you. The pace slows further. We are very deep in the night now, very close to sleep. The Archean is 1.5 billion years of experiment. of variation and selection and adaptation and diversification, running simultaneously across an entire ocean, in every chemical environment available, trying every possible strategy for extracting energy from a world that is both resource and challenge. Most experiments fail. Most mutations are harmful or neutral. Most lineages that begin in the Archean do not survive to the present. The tree of life has many dead branches that flourished for a time and then were outcompeted, or could not adapt when their environment changed, and disappeared without descendants. But enough survive. Enough adapt. Enough carry forward the accumulated innovations of their ancestors, the membrane, the genetic code, the metabolic strategies, the capacity for photosynthesis to build, over the next several billion years, the full extraordinary diversity of life on Earth today. Every innovation builds on what came before. Every organism alive today is the beneficiary of 4 billion years of accumulated biological ingenuity, most of it anonymous, most of it microbial, most of it occurring in the dark and the deep of oceans that no human eye has ever seen. You are the sum of all of it. Very slow now. Almost a whisper. The cells of your body are eukaryotic complex, nucleated, the product of that ancient merger in the Archean Sea. Your mitochondria still carry their own DNA, a remnant of the time when they were free-living bacteria, before the merger that made complex life possible. Every time your body generates energy, every breath, every heartbeat, every thought, it does so using machinery inherited from that ancient bacterial partner, refined over 2 billion years of evolution but recognizably, molecularly, the same. You are an experiment that has been running for 4 billion years. And so far, it is going rather well. Let the thought of that settle softly over you, like sediment drifting down through warm water. Let it be the last clear thought before sleep takes you, the quiet, astonishing fact of what you are. How old you are, in your deepest parts. How many generations of patient, blind, tireless life have contributed to this moment of you lying here, breathing, existing. For billion years. One long experiment. And here you are. Every chapter has a last page. Not an ending, exactly. The story does not stop. The characters carry forward. The world continues, as worlds do. But there is a moment when the conditions that defined a particular era have shifted enough that what comes next is recognizably different from what came before. When the accumulated weight of gradual change becomes a threshold, and the threshold is crossed, and the world that emerges on the other side is not the same world that entered. The Archean is approaching such a moment. It has been building toward it for hundreds of millions of years, slowly, invisibly, in the chemistry of the ocean and the biology of the microbial mats and the patient accumulation of oxygen that has nowhere yet to go. The fuse, lit by the first cyanobacterium that split a water molecule and released its oxygen as waste, has been burning for longer than the entire span of animal life on Earth. It is almost ready to reach its charge. But before it does, before we stand at the threshold of the great oxidation event and watch the world transform, let us take stock of where the Archean has brought us. Let us look at the late Archean world in its fullness, 2.5 to 3 billion years ago, and see what this extraordinary eon has built. The late Archean Earth is a world in transition. Not visibly, not dramatically to any observer capable of standing on its surface and looking out, it would appear much as the early Archean did. Dark volcanic rock. A warm, brownish-orange sky still thick with greenhouse gases, still lacking the oxygen that would one day make it blue. An ocean stretching to every horizon, still rusty with dissolved iron in some regions, still warm, still chemically unlike anything that will exist in later eons. But beneath that familiar surface, everything has been changing. The continents are larger now. The scattered islands of the early Archean have coalesced through the long process of terrain accretion, of craton collision and welding into something approaching genuine landmasses. Several major Archean cratons are now significant continental blocks, and the evidence suggests that by the late Archean, around 2.7 to 2.5 billion years ago, they are beginning to assemble into something even larger. The first supercontinent. The existence of a late Archean supercontinent or something approaching one is a matter of ongoing research and debate. The evidence is fragmentary, the paleomagnetic data difficult to interpret at these ages. But a growing body of work points to a significant episode of continental assembly around 2.7 billion years ago, a time when the geological record shows a pronounced pulse of new crustal formation, a burst of mountain building, of granite emplacement, of the geological activity that accompanies continental collision on a large scale. Some researchers have proposed a supercontinent they call Valbra, assembled from the Karpval Craton of southern Africa and the Pilbara Craton of western Australia, among others, perhaps the oldest supercontinent in Earth's history. Others point to a larger assembly called Kenneland, incorporating the Superior Province of North America, the Kola and Karelia Cratons of what is now northern Europe, the Hearn and Ray Cratons of northern Canada, perhaps others. The details remain uncertain. The names are provisional. But the broad picture seems increasingly robust. By the end of the Archean, the Earth's continental crust is not scattered in isolated fragments across a global ocean. It is gathering, assembling, coming together in the first of the great supercontinent cycles that will repeat themselves across the next 2.5 billion years of Earth's history. Kenneland, Columbia, Rodinia, Gondwana, Pangaea, and whatever comes next, each one a gathering and a dispersal, a making and an unmaking, driven by the restless convection of the mantle below. The Earth is learning a rhythm. The rhythm of assembly and dispersal that will beat at the heart of her geology for as long as she remains geologically active. The late Archean also sees a significant change in the style of volcanism and tectonics. By 2.7 billion years ago, the evidence for subduction, for the diving of oceanic crust beneath continental margins, with its associated volcanic arcs and metamorphic belts, is clear and widespread in the rock record. The transition from whatever earlier regime operated in the hot, chaotic early Archean to something recognizably like modern plate tectonics appears to have been largely complete, or nearly so, by this time. The mantle is cooler than it was. Not dramatically, it is still hotter than today, still producing komatiites in places, still running a more vigorous convective engine than the modern Earth. But the difference from the early Archean is real and measurable, in the rock types preserved, in the style of deformation recorded in the ancient mountains, in the chemistry of the volcanic products. The Earth is maturing. Her interior is slowly, irreversibly cooling. The heat of formation and of radioactive decay is gradually bleeding away into space, and the loss of that heat is changing the character of her geology. The planet that erupted komatiite flows like rivers of liquid rock is becoming, slowly, the planet whose volcanoes produce the thicker, cooler, more gas-rich lavas of basalt and andesite. The planet whose crust was too thin and too hot to sustain rigid plates is becoming the planet of the great tectonic dance. She is becoming more like herself, more like the Earth we know, with every passing million years. The atmosphere, too, is changing. Still anaerobic, at 2.5 billion years ago, lacking any significant concentration of free oxygen. But the methane that dominated the early Archean greenhouse is being slowly processed. The cyanobacteria are producing oxygen, and though most of it is still consumed by iron in the ocean, some of it reacts with the atmospheric methane, breaking it down, reducing the greenhouse warming that methane provides. This is a delicate moment. The loss of methane from the greenhouse, without an equivalent rise in CO or a significant brightening of the sun, risks tipping the climate toward cooling. And indeed, there is evidence that the very latest Archean period, right at the boundary with the Proterozoic, saw significant glaciation, possibly global in extent. The Great Huronian Glaciation, which would be the most severe cold episode Earth had yet experienced, is beginning to take shape at the very edge of our story. The cyanobacteria, in producing oxygen, are inadvertently dismantling the greenhouse that has kept the Earth warm. They do not know this. They are simply doing what they do. But the consequences will be enormous. Stand back from the Archean for a moment, and look at it whole. For billion years ago to 2.5 billion years ago. 1.5 billion years of time. In that span, the Earth has gone from a world of liquid rock and poison gas to a world with stable oceans, growing continents, a functioning magnetic field, a developing tectonic system and life. An entire biosphere, invisible to the naked eye, microbial, diverse, metabolically inventive, spread through every available environment from the deep ocean floor to the shallow sunlit margins of the first continents. The Archean has built, in essence, a living planet. Not the living planet we know, not the blue and green and teeming world of the present day. But a living planet nonetheless. A world where chemistry and biology are inseparably intertwined, where the oceans are shaped by the organisms in them, where the atmosphere is being slowly altered by the metabolic activity of countless trillions of microscopic lives, where the very rocks record the presence of organisms in the isotopic signatures left behind. Life has not merely arrived on this planet. It has become part of the planet. It has woven itself into the Earth's chemistry so thoroughly that the two can no longer be meaningfully separated. This, in a sense, is the great achievement of the Archean. Not any single organism, not any single event, but the weaving of life into the fabric of the Earth so completely that the world that follows is a fundamentally different kind of world from the one that preceded it. A world with a biosphere. A world that is, in the deepest sense, alive. And at the edge of the Archean, in those late millions of years before the boundary at 2.5 billion years ago, the fuse reaches its charge. The iron in the ocean is not inexhaustible. Billions of years of cyanobacterial photosynthesis have been converting dissolved ferrous iron into iron oxide, precipitating it as the banded iron formations that stripe the ancient rock record in vivid red and gray. But the supply, vast as it is, has limits. And as the Archean nears its end, those limits are approaching. In places in the shallowest, warmest, most productive waters the iron is running out. The oxygen produced by the cyanobacteria has nothing left to react with. And so, for the first time, in small patches and briefly at first, oxygen begins to accumulate in the water and escape into the atmosphere above. It is not yet the great oxidation event that comes early in the Proterozoic, perhaps 2.4 billion years ago. But the oxygen is beginning to leak. Beginning to seep into an atmosphere that has never contained it in significant quantities. Beginning, for the first time, to make its presence felt in the chemistry of the air. The world is about to change in a way that dwarfs everything we have described so far. The great oxidation event will transform the atmosphere, the ocean, the chemistry of the surface, and the trajectory of life itself. It will kill the majority of the organisms then living on Earth for oxygen. To an anaerobic organism that has never encountered it, is not the life-giving substance we know but a deadly poison, as reactive and destructive as fire. It will be the greatest extinction that has ever happened. And it will be caused by life itself. But that story belongs to the next chapter. The Proterozoic has its own episode waiting to be told, its own billion years of consequence and transformation. For now the Archean is complete. 1.5 billion years. Let that rest with you for a moment. Not as an abstraction, not as a number to be understood intellectually, but as a felt thing. A duration. A span of time in which everything we have described tonight unfolded: the first rains, the first rock, the first cell, the first photosynthesis, the slow growth of continents, the long diversification of microbial life, the patient accumulation of oxygen in the deep waters of an iron-rich sea. All of it happened. All of it was real. And all of it led, through an unbroken chain of consequence and continuation, to this moment, to you, lying here, in the dark, breathing air that did not exist until life made it, resting on rock that formed in fire, alive with a complexity that took 4 billion years to assemble. The Archean is over. But it is not gone. It is underneath everything. It is the foundation. It is the first chapter of a very long book, and every subsequent chapter rests upon it. Without the Archean, there is nothing. And because of it, there is everything. Rest now. The chapter is closing. The next one will begin in its own time, when you are ready for it. For now let the Archean hold you. Let 4 billion years of patient, improbable, irreplaceable becoming be the last thing your mind rests on before sleep carries it somewhere else entirely. The Earth made it through. And so did you. We have been traveling a long time tonight. Not in miles, in years. In billions of years. In a span of time so vast that the human mind cannot truly hold it, but can feel the edges of it, can sense its weight, can let it settle like something large and gentle over the smaller concerns of a single day. We began in fire. In a world of liquid rock and poison gas and the terrible beautiful violence of a young planet finding its shape. We watched the rains come for the first time, filling the basins of the new crust with water that would not leave, that would become the ocean, the same ocean that exists today, older than any mountain range, older than any continent in its present form, older than almost everything. We watched the first rock solidify. The first craton form. The first tiny patches of pale, buoyant granite rising above the ocean surface, battered by storms, bare of anything living, but there. Present. Real. The beginning of ground. We watched, or rather, we imagined, we inferred, we reconstructed from the patient evidence of ancient stone the first flicker of life. Chemistry crossing a threshold into something more than chemistry. The first cell, the first membrane, the first molecule that could copy itself and thereby begin the long, extraordinary experiment of evolution. We watched the stromatolites build their quiet reefs. The cyanobacteria lift their invisible oxygen into the water. The banded iron formations accumulate in their slow, beautiful layers. The continents gather themselves from fragments into something approaching landmasses. The mantle cool, imperceptibly, degree by degree across 1 billion years. We have watched the Archean. And now it is over. What did it leave behind? Not a question with a single answer. Not a question with a short one. But let us try, here at the end, to name the things the Archean gave to everything that follows. The inheritance. The foundation. The gifts, freely and unknowingly given by a world that had no concept of giving. It left the cratons. Those ancient, pale, grey-pink hearts of continent, sitting still at the cores of every major landmass on Earth: the Canadian Shield, the Siberian Platform, the West African Craton, the Pilbara, the Yilgarn, the Kartval, the Dawa of India, the São Francisco of Brazil. Billions of years old and still there, still solid, still holding up the younger rock piled upon them, their deep lithospheric keels anchoring them against the drift of the mantle currents. They are the oldest solid things on Earth's surface. The Archean's most durable gift. It left the banded iron formations. Those extraordinary layered rocks, red and grey, chert and iron oxide, patient accumulations of billions of years of cyanobacterial oxygen reacting with oceanic iron, which today are the source of most of the world's iron ore. The steel in a bridge, in a ship, in the frame of a building, it comes, in enormous proportion, from Archean banded iron formations mined in the Pilbara of Australia, the Harmusley Basin, the Iron Ranges of Minnesota and Michigan, the Carajas deposit of Brazil. The infrastructure of the modern world is, in a very real sense, built from the exhaust product of Archean microbial life. Every time you cross a steel bridge, you are crossing on the work of cyanobacteria. 3 billion years ago. It left the gold. The ancient placer deposits of the Witwatersrand, laid down in Archean rivers draining Archean mountains that no longer exist. Gold that has been sitting in that rock for 3 billion years, waiting. Gold that powers electronics, preserves wealth, decorates ceremony. Gold older than anything complex that has ever lived. It left the genetic code. The deep, universal machinery of life: the ribosome, the codon table, the double helix, the cell membrane, all of it established in the Archean, all of it inherited by every organism that has lived since. Every bacterium, every fungus, every plant, every animal, every human being operates on Archean software. The code has been annotated, expanded, modified in countless ways across 4 billion years of evolution. But the core is Archean. The core has not changed. It left metabolic strategies. Fermentation, sulfate reduction, methanogenesis, nitrogen fixation, photosynthesis, all of these biochemical capabilities were invented in the Archean Ocean, by organisms that no longer exist in their original forms but whose inventions have been passed down, conserved, elaborated, built upon. Every metabolic process in the biosphere today has its roots in the Archean. Every crop plant fixing nitrogen in its root nodules is running a process first developed by Archean bacteria. Every animal breathing oxygen is consuming the product of a cyanobacterial invention 3 billion years old. It left the oxygen. Not yet present in the atmosphere at the Archean's end, still just beginning to accumulate, still just beginning to make its first tentative appearance in the chemistry of the air, but the process is unstoppable. The cyanobacteria will not stop. The iron in the ocean is nearly exhausted. The oxygen is coming, and when it comes it will transform the world more completely than anything since the formation of the planet itself. The Archean loaded the gun. The Proterozoic will fire it. Every breath you take tonight draws on that inheritance. The 21% oxygen in the air around you is the product of billions of years of photosynthesis, begun in the Archean Sea, continued without interruption to this moment. The Archean breathes in you. Literally. And it left the ocean itself. The same water, cycling and recycling through evaporation and rain and river and sea, that fell on the young Earth as the first rain 4 billion years ago. Water molecules are not destroyed, they are rearranged, broken apart and reformed, but the hydrogen and oxygen atoms persist. Some of the water molecules in the ocean today have been in that ocean since the Archean. Some of the water in your body tonight has been on this planet since before the first cell existed. The Archean Ocean has not ended. It has simply continued, age after age, changing its chemistry and its temperature and its biology, but always present, always liquid, always the medium in which the chemistry of a living planet runs. There is a particular quality to thinking about deep time at the end of a long evening. When the thinking is not anxious or urgent but slow and receptive, when the mind is at that soft, open threshold between wakefulness and sleep where the ordinary boundaries of self and world become a little less distinct. In that state, the distance between 4 billion years ago and tonight does not feel quite as absolute as it does in the ordinary transactions of the day. The Archean feels close, somehow. Not because it is unimaginably distant, but because it is present. Because it is here, in the rock below and the air around and the cells within. Because the distance is not empty space but an unbroken chain of continuation, of life and rock and water passing forward from moment to moment without interruption. You are at the end of that chain. Or rather you are the latest link in it. There will be more links after you, more continuation, more of whatever extraordinary experiment the universe is running with this particular planet. But tonight you are here. The latest arrangement of atoms that have been on this planet since before the first morning. The most recent expression of a story that began in fire and has been told, without pause, across 4 billion years. The Archean does not end. Not really. The eon boundary at 2.5 billion years ago is a human designation, a line drawn in the rock record at a point where the evidence of change is pronounced enough to mark a new chapter. But the Earth herself does not recognize chapters. She does not pause, does not reset, does not begin again from nothing. She continues. The Proterozoic follows the Archean not as a replacement but as a continuation. The cratons carry forward. The ocean carries forward. The biological lineages carry forward, transformed by the oxygen revolution that is coming, but carrying within them the deep ancestral machinery of Archean chemistry. Everything the Archean built is present in the Proterozoic, as the foundation is present in every floor laid above it. And the Proterozoic will carry forward into the Paleozoic, and the Paleozoic into the Mesozoic, and the Mesozoic into the Cenozoic, and the Cenozoic forward into whatever the next chapter is called, the chapter that contains us, that is still being written, that will be read, perhaps, by whatever kind of mind exists to read it millions of years from now. The story does not end tonight. It never ends. But this episode of it, the Archean, the first chapter, the long and patient and extraordinary beginning, this has been told. Thank you for traveling with the Earth tonight. For sitting with the deep time. For letting the fire and the rain and the dark ocean and the quiet microbial mats and the growing continents move through your mind on their way toward wherever thoughts go when sleep takes them. The Archean is over. The rest of the story is waiting. But not tonight. Tonight only this. The oldest rock, somewhere below you, holding everything up. The ocean, somewhere beyond you, still running the same cycles it has run for 4 billion years. The oxygen in your lungs, produced by life, breathed by life, the gift of cyanobacteria who never knew they were giving it. The cells of your body, carrying within them the molecular memory of the Archean, see the ribosome, the membrane, the ancient mitochondrion with its bacterial DNA, all of it inherited from a world that ended 2.5 billion years ago and yet is still entirely present in everything alive. You are the Archean, continued. You are the story, still being told. And tonight, the story rests. This concludes the video. Thanks for watching. Sleep well. Good night.